Distinguished guests, professors, scholars, laureates, ladies and gentlemen, and all the friends in front of the camera, good evening. Welcome to the ICBS International Congress of Basic Science 2026 Physics Night in Peking, China. I'm Grace Liu, feeling so privileged and lucky to spend this wonderful night with the world's most brilliant minds here. By hosting tonight's festivity. To kick it off, please join me in welcoming the chairman of the Congress, chair professor at Tsinghua University, foreign academician of CES, Professor Xintong Yao, to the stage to give us the opening remarks. Welcome.
Well, it was exciting to see all these major scholars getting the awards this year. So it is new that we set up 3 scholars per field. So in the case of physics, we have 3 distinguished scholars who got the award. So as you know, one is named after Professor Ding Zhaozhong, one of the greatest experimental physicists. And we congratulate Wang Yifang got the award. Then there's David Gross award, which is one of the most distinguished theoretical physics, high energy physics, who got the Nobel Prize, a good friend of mine actually. So we are very happy that he allowed us to use his name for both Professor Ding and Professor David Gross. And also this year we set up an award mostly for women, and we are extremely happy that the descendants of Madame Curie allow us to use her name, which is one of the most appropriate, distinguished Nobel laureate in both physics and chemistry. So I'm very happy that all the scholars who got the award are truly remarkable, has made most accomplished career in their life. So we do the same thing in mathematics and also engineer. So 9 awardees, all of them are really truly remarkable mathematicians and physicists and also engineer. So Wen Xiaogang got the David Gross Award, but in many cases he's used mathematics ever since he was student of Ed Witten, who I know well. As I said this morning, Witten mid-1980s produced several truly distinguished students, including Wen Xiaogang and Konrad Marfa and several others, who later built the string theory as a truly important subject in both physics and mathematics. I think it's really important that we can understand each other. In the last 50 to 70 years, there's a really close matching between mathematics and physics. And I think mathematics without physics will lose a lot of beautiful intuition that come from our physics friends. And I believe physics without mathematics will not be like what is it now. The computation is far more complicated than what physicists would do in the 1950s and before. Now we need much more complex arguments that depends on mathematics. So the true collaboration between mathematics and physics are really remarkable, I think. And of course, we saw and Andrew Liu got the Madame Curie Prize, and I think it's very remarkable also, her work. And it's also very interesting from the point of view of mathematics. So I mentioned that because I think when I set up this conference, this Congress, International Congress for Basic Science, was meant to kind of put three different important fundamental sciences together. So physics, mathematics, and engineer. And we interact with each other, we learn from each other, and I think this really has been fruitful. Personally, I learned a lot from the awardees in the last 3 years, including this year, 4 years. And there are many things I want to explore myself. And I believe the students learn a lot from all these distinguished scholars, which otherwise would not be possible. Through this Congress, I can learn directly firsthand from the people who got the award, and they are willing to give a detailed explanation of what they do. Otherwise, I probably would never have been able to learn what they do. And indeed, I think I learned very much in this way. And of course, besides listening to the lectures they gave, individually, we have many people, younger people who got the Frontier of Science Award, and we have been listening to their lectures. I think this is very important. I actually, although I was very busy, I've been going to these lectures given by Frontier of Scientists lectures. They are the most advanced lectures that are in the field. That has been very inspiring. And I have no other chance besides this Congress that I was able to listen to them. So I think our Congress has played a very important role besides recognizing truly distinguished scholars, but we also facilitate the interaction between different fields. And I think this should go on and will build a truly remarkable platform for our distinguished scholars and the students and postdocs come together and celebrate what is done in the last few years. So far, we are doing very well with what we have done. Fortunately, President Xi has announced basic science is an important subject for the country 3 months ago. So this Congress is now being respected much more now by the government. So we see the party secretary of Beijing City come to chair this Congress. And I think this is a very important indication that basic science will be supported by the government. And I hope everything goes well. And many important events has been accomplished, including the Jiaoqiu, the gluon sphere, is a gluon ball discovery. I was just learned. It's a remarkable discovery. I think this is very important. So theoretical science are, of course, important, especially with the help from AI. Everybody is talking about how important AI is. And mathematics is also now influenced by AI. Some theorems were discovered by AI. All these are very important. But I think the mystery of nature is infinite. No matter how we try, whatever AI, how powerful the machine is, we can only master a finite amount of knowledge. For us to understand the infinite mystery of nature, it would not be possible. Only through experiment, through observation, we will increase our knowledge about nature. So I truly admire the important achievement by our experimental physicists, although I'm completely ignorant and incapable to do that myself. But I think with the cooperation by mathematicians, by theoretical physicists, and by experimental physicists, and by engineers, we will build a truly important family here. Thank you.
Thank you, Professor Yao, under whose leadership this Congress has attracted more and more attention, become more and more diverse and influential. We do appreciate that. Now let's invite our next speaker, the director of the Institute of High Energy Physics, Professor Jun Cao, to give us his welcoming speech. Welcome.
Good afternoon, respected Professor Xintong Yao, distinguished guests, colleagues, and young researchers. It's my great honor to extend my warmest welcome to everyone joining the 2026 ICBS Physics Night. It marks the fourth edition of Physics Night hosted by the Institute of High Energy Physics, or IHAP. The vision of our institute is to become one of the world's leading particle physics research centers and a large, world-class, comprehensive, multidisciplinary research base. As a distinctive academic salon, the Physics Night offers an excellent opportunity to bridge the disciplinary divide in physics. We owe this gathering to the International Congress of Basic Science, which brings together leading minds from across the globe. For more than 50 years, IHAP has stood at the forefront of large-scale scientific undertakings. Since 1988, IHAP has constructed and operated China's first largest science facility, the Beijing Electron-Positron Collider. To this day, the collider continues discovering new particles and new phenomena. As mentioned by Professor Yao just now, only a few days ago, the Bess-Ray experiment on the collider confirmed the existence of globe, an entirely new type of particle in nature composed of force carriers, which scientists have sorted for half a century. IHAP runs a highly successful neutrino research program with the Diabase and Juno experiments. We are also vigorously advancing high-energy frontier physics research through participation in the LHC experiment in Europe and the promotion of the CEPC project in China. Our contributions span across multiple research frontiers. We pursue astrophysics studies via satellite missions, including InSight, GCAM, Einstein Probe, and so on. We host the NASO, the world's most powerful ground-based cosmic ray observatory, and ANICPT, a ground-based cosmic microwave background observatory. Meanwhile, we operate a spallation neutron source in Dongguan, the south of China, and the world's brightest synchrotron light source, situated just a few kilometers away from here. Today's scientific breakthroughs increasingly arrest at the interdisciplinary boundaries, and no single research field can advance in isolation. Tonight, we bring together researchers across many frontier directions. Diverse as this field appear to be, they share the same core mission to the universal logic of nature. Modern physics is highly interconnected. Discoveries in elementary particle physics deepen our understanding of cosmic evolution. Quantum material theories provide a new perspective for biological collective behaviors. Mathematical tools from string theory and gravity research continuously empower innovations in condensed matter physics and precision biophysics studies. In the hour ahead, we will witness a series of insightful academic presentations covering the full spectrum of interconnected physics frontiers. This event is specially arranged to offer a credible, relaxed atmosphere for communication. I highly encourage young students and early career researchers to engage actively with top scholars, exchange innovative ideas, and foster potential cross-disciplinary cooperation for the future. I wish to express my sincere gratitude to the ICBS Organizing Committee for establishing this invaluable cross-field exchange platform, and to all distinguished scholars for sharing their profound insights with us. I greatly look forward to tonight's boundary-breaking intellectual journey and inspiring academic exchanges. Thank you very much, and welcome to Physics Night 2026. And in the next session, we will have three keynote speakers to do the presentation. So it's my great privilege to introduce these three keynote speakers. The inaugural laureate of the 2026 ICBS Basic Science Medals in Physics, whose groundbreaking research spanned disordered soft matter, experimental neutrino physics, and topological quantum theory. Each will deliver a keynote lecture presenting their transformative discoveries and forward-looking scientific vision. So our first speaker will be Yifang Wang. We slightly change the order. The recipient of the 2026 ICPS Samuel Ting Medal in Physics. Professor Yifang Wang is working at the Institute of High Energy Physics, Chinese Academy of Sciences. He received the Samuel Ting Physics Medal for revolutionary experimental breakthrough in neutrino oscillation physics. As the co-spokesperson of the Daya Bay reactor neutrino experiment, his team made the world's first precise measurement of neutrino mixing angle θ13, uncovering a new neutrino oscillation mode and finding the critical missing parameters of the neutrino flavor mixing matrix, laying core groundwork for solving cosmic matter-antimatter asymmetry puzzle. Currently, he's leading the Juno experiment with the world's largest liquid sentinel detector designed to resolve the long-standing problem of neutrino mass ordering and search for new physics beyond the standard model. He also leads the design and R&D of the Circular Electron Positron Collider, or CEPC, a next-generation Higgs factory. His landmark contributions has earned him a string of top-tier global honors: the APS Panofsky Prize in Experimental Particle Physics, Breakthrough Prize in Fundamental Physics, Bruno Pondakov Prize, and the Future Science Prize in Physical Sciences. He has established Asia's flagship infrastructure for global neutrino physics collaboration and elevated China's standing at the frontier of high-energy physics. So let's welcome Yifang Wang to give the keynote presentation.
Distinguished Professor Yao, ladies and gentlemen, it's a great honor for me today to deliver these presentations. I extended a little bit the scope of my talk, not only neutrinos, but also all the possible portals of new physics. This will facilitate a little bit the following discussion, the panel discussions. So the main portals of new physics, this is just a view from a particle physicist. First of all, it's hadrons and the flavors. We have BESRI in China and some other facilities in the world, which studies quarks, taus, and the gluons. The second one is neutrino. We have Juno in China and many others in the world. And the third one is Higgs. We are planning to build CPC in China, hopefully. And also we are working on the Atlas CMS at CERN. There are also other facilities in the world, FCC at CERN and IS in Japan, the Muon Collider in the US. They're trying to study the Higgs, the Z's, and W's. And of course, we try to looking for something beyond the standard model. So which direction, we have no idea. There are many tries, so exotic searches, astrophysics, cosmology, and also maybe new opportunities enabled by, say, future technologies. Let's go one by one. So we're talking about particle physics. It has been started around the 50s when hundreds of new particles were discovered. And in 1994, Gell-Mann and others postulated that these particles are actually made of more fundamental elements, the quark. So in his quark model, there are three types of quarks, up, down, and strange. And there are two types of hadrons, meson and the baryons. So you can easily ask a very simple question. Why only two types of hadrons? And why only three types of quarks? So these are the efforts we have been working on since then for almost, say, 70 years. First, let's see what we have achieved at the BEPC, the Beijing Electron Positron Collider. Has been started the construction in the 1984 up to 1988 for only 4 years to finish the construction, which is also the remarkable achievement considering China, who never built a large accelerator at that time. And this was also the beginning of the particle physics in China. It's also the foundation for other large facilities in China, like the Beijing Synchrotron Radiation Facility, the Shanghai Light Source, the China Spallation Neutron Source, and also high energy photon source, which is only a few kilometers from here. And later on in 2004, we built this upgrade. Now we call it the BEPC2 and BESS3. And in BEPC2 and BESS3, you can see from this figure, it's a continuation of the luminosity increase from, let's say, 10 to 29 all the way up to 10 to 33, so almost 4 orders of magnitude. And you can see that China has been continuing to increase and working on this energy range for almost 40 years. And BESS3, indeed, in the last 18 years, have discovered 33 new hadrons, which is a large number. Recently, I just got the number from CERN. They have discovered all the 4 experiments, Atlas CMS, HCP, and so on, combined 85 new particles. So a small experiment here, we are almost, let's say, half or maybe 1/3 of all the HC experiment combined. So it's not a small number, let's say. And with more statistics at the same collider, 4 orders of magnitude increase of luminosity, you can see that we see a lot more new particles, not just because of energy, but also statistics. In 2005, with the 58 million of GPSI, we see this new particle discovered at BESS2 called 1835. Later on, with 200 million GPSIs, we see 2 more peaks, one of which is X2370 in the year 2011. And over the time, with 10 billion GPSIs, we got a lot more, let's say, peaks and much less statistical fluctuations. And by detailed study of these particles using 10 billion GPSIs about this X2370, we realized that this is what we were looking for, the lattice QCD predicted glue bond. And its existence indeed is a test of QCD because it's made of gluon only. This is the only particle which are made of, let's say, force or mediators, not by fermions. All the matters we're seeing up to now are made of 12 fermions, but this is the only one made of, let's say, force particle. And we have been looking for 50 years, and now we see it here. And this is actually 40 years effort of BPC BESS3 over several generations of people, equipment, and also the effort. There are many other discoveries at BESS3. It's multi-quarks. The ZC3900 has been observed in 2013. This is actually the first ever well-confirmed multi-quark states before the pentaquark, you all know, which was 1 year later by HCB. And its neutral and the higher mass companions soon discovered and confirmed also by other experiments and many other partners like the ZCS, charged and the neutral ones. So you can see an old machine running for 40 years can actually produce a lot of new discoveries and new states. Another one is hybrid, which is a quark, antiquark plus gluons. And using 10 billion JIP size, we also see that this particle has a JPC which is not possible for normal mesons. So it must be something new beyond the quark model predicted by German. So BPC2BESS3 will continue for another 10 years at least to further increase luminosity and also test technologies. The main physics topics, including XYZ, JIP, charm barons, and the R scans, and so on. So you can see that this accelerator will have a lifetime of 50 years, which is probably the only one in the world up to now. And a very good choice, I would say, by Li Zhendao, T.D. Li, in the beginning of 80s. So a remarkable choice for particle physics in China. And I would say this is also a great decision by Deng Xiaoping at that time, which was not easy, with a lot of oppositions, and indeed a great political decision can make our science with a great success. So let's look for the second question, how many quarks? So there were 3 at the time of German. And soon after, in 1974, roughly 10 years after, Samtin and Bouton Richter discovered the JIP psi. This is the 4th quark. And then we had the 5th, Ledman discovered the B quark. And lastly, there is a top quark in 1995 by CDF. There are also leptons. The first one is electron, which was discovered in 1897. It's a long time ago. Actually, the first elementary particles discovered by mankind. Secondly, we have muons, and then we have electrons, electron neutrinos, and then we have a muon neutrino, and afterwards we have tau and also the tau neutrino. So you see, we have a beautiful picture that we have quarks and leptons. They are very symmetric, I'll say. And you can easily ask the question, do you have the 4th generation from UCT, and do you have a next one? Indeed, in 1990 at the lab, many experiments, including the one led by Professor Ting, that there are only 3 generations, no more. Of course, it makes our life much easier, but on the other hand, pose the question, why only 3, and why the word elementary particle physics are so simple? So this is whatever we have, current standard model. We have a very symmetric kind of fermions, symmetric, 6 quarks, 6 leptons. And then we have intermediate, let's say, force, intermediate particles for the force. So we have photons, WZ, and gluons. And lastly, we have Higgs, which was discovered in 2012 by the HC experiment, and also the two big detectors you can see here, ATLAS, and there's another one, CMS, which discovered simultaneously the Higgs particle. Of course, together with many Nobel Prize. So the current international consensus about the particle physics or Standard Model is that Higgs is actually the last puzzle of the Standard Model, but it's not the completion of the Standard Model itself. Standard Model is only the effective theory up to roughly 1 TeV. So the International Committee for Future Accelerators concluded that the Higgs factory is the highest priority for realizing scientific goals of the particle physics. It's the top priority for the future of our field. So there are several proposals, let's say CPC in China, FCC at CERN, IRC in Japan, and also CLIC at CERN. So we were not absent in this case for the race of the next generation of particle accelerators. Rather, we were leading the effort. We are the first to propose circular collider as a Higgs factory, because this is actually much better than, say, a linear collider. So indeed, our effort lead us to be, let's say, the leader of the field. Why it's important? The Higgs actually plays important role in many ways. Let's say origin of electrical symmetry breaking, natureness problem, early universe, and in particular, maybe it's a bridge to dark matter, because we know that dark matter has only one property, which is a mass, and the Higgs generate the mass for normal particles. What is its connections with dark matter mass? So there's a very number of the imaginations you could have to understand the dark world and also to understand the connection through Higgs. Our effort in the last, let's say, 13 years has been enormous. Starting from the kickoff in 2013, we generated our conceptual design report, technical design report for both accelerator and detector, and now we are working on the so-called engineering report. And we believe we are ready in a few years from now, let's say 2, 3, maybe 4, to start construction. Hopefully, it can be approved by the government. But unfortunately, it was not. So what's next? So CPC, we finished our design, and we have these essentials. The same terminal is going to be host the E+- collider as a Higgs factory, and also possible future upgrades for PP collider and also for the EP collider. The baseline is roughly 100 kilometers, 30 megawatt of the synchrotron radiation power, but can be upgraded to 50 megawatt, high lumen Z and TD bar. So you can see that these numbers are very similar to FCC, or in other words, indeed, FCC had very similar parameters with CPC. In addition, this machine can be a very advanced synchrotron radiation facility. You can see the light, which have a very high energy and high flux, compared to all the international high energy gamma source. So indeed, this machine is not only for basic science, but also for applications of future gamma source applications. There were a lot of people talking about how expensive this machine is, and people were talking about tens of $1 billion, but indeed, this is a very serious and the professional calculation of the cost, which is 36 billion RMB, which is roughly $5 billion or euros, a factor of 3 cheaper than what you have to spend at CERN for the FCC. So we believe this is a very good choice for China and a very good choice for our field. Unfortunately, some of you probably know that it was not put into the construction for the next 5 years. So what's next? Our vision for the future actuator is the following. We believe both the circular 100 kilometers Higgs factory, this is what we propose, and also the linear collider of 30 kilometers proposed by Japan are available now for construction. So these are the available technologies. The reason we choose these two, you see, is technology, the cost, and also the energy efficiency. That's why we choose the circular collider, the CPC, which we believe is better than the linear collider. But we don't really, let's say, forget about the linear technologies. So we are actually working on the future technology for both the PP collider and the very, very high energy linear collider using the plasma weak field actuator technologies and also energy recovery LINAC. So we are actually working on both, while we are working with CERN, trying to be a partner of the SEC, but we are also going to work by ourselves for the next generation particle actuators. Now let's move to neutrinos, which is the main theme of today. And we all know that neutrino is a clear evidence beyond the standard model. Neutrino oscillation is clear evidence beyond the standard model, and we should look for what could be the new theory. There are a number of experimental questions and also their physics implications, including, for example, neutrino ordering and mass ordering, CP phase, number of generations, star neutrinos, double beta decays, etc. And they are all connected fundamental physics questions about, let's say, matter-antimatter symmetry in the universe, the extension of the standard model, how to restore the parity violation at a weak scale, and how to modify standard model if we know we had to have a mass term in the Lagrangian, and also very much related to the cosmology-related issues. So all these kind of possible new models or new theories need new experimental evidence. And the React neutrino is a great tool. It has been the tool for the discovery of the neutrino itself, and also the neutrino mixing parameters, okay, CT12 and the datam21, CT13 are all measured for the first time at reactors. And now it's going to be help us determine the mass ordering, and in the future, it will help us to work on the neutrinoless double beta decays. This is the beginning of react neutrino physics in China, that's Diabei, which observed for the first time the mixing angle CT13, and this actually signals the existence of the new type of the neutrino oscillation. The next step is actually the Juno experiment, which is just running right now. This is a continuation of our effort using react neutrinos because it's relatively cheap, and also using the liquid scintillator. Again, it's a cheap material for neutrino detection. The idea came since 2008. It took us almost 18 years up to today to have this detector running. The detector is located here, which is 53 kilometers from 2 nuclear power plants in Taishan and Yangjiang, with the world's largest thermal power for the neutrino flux. And if you compare the other experiment with a similar kind of properties using liquid scintillator, you can see that we have the highest mass and the highest possible light yield and best the energy resolution, because it has to be 53 kilometers from the reactor, which is a pretty large, let's say, baseline, and generate a lot of complications for us as experimental physicists. This is a picture of the detector. You can see clearly the critical tank containing liquid scintillator inside, 20 kilotons, supported by the steel bars, and then the PMTs are installed on this steel structure. And the clearance between these PMTs, you cannot see it, but I can tell you this is about 3 millimeters, which is the smallest possible you can imagine, but still safe even during the earthquake. This is a picture of all the PMT installed. See the acrylic tank and PMTs, a total of 20,000 20-inch PMTs that's been installed in this detector, plus another 25,000 3-inch PMTs in between the 20-inch. So we got our first results for 59 days of data taking. The results have been published, and now we have the new results using 207 days of data. I can show you a few of the new results. So this is our measurement of solar oscillation parameters, DATM21 and the theta12. You can see that this is our new measurement, and this is our old measurement. You can see we improved by only a factor of 4 statistics, significantly reduced uncertainty. And these are other measurements in the past by reactor and by the solar neutrinos. You can see they differ by roughly 1.8 or even 2 sigma. And now our measurement is roughly in between. We believe that react neutrinos and the solar neutrinos give the same oscillation result, which is very, very important because solar neutrinos is neutrinos and the react neutrinos are antineutrinos. If they are different, it means that the CPT is violated. This is a very, very important, possible consequence. But fortunately, I think we believe CPT is conserved from this data. We also measured for the first time the DATM31 with a precision of 1%. This is about 40% better than the best measurement up to now. And using this number, we can determine the neutrino mass ordering. And you can see that we see this difference. This is about 2.3 sigma preference for the mass ordering. In the future, this experiment can be converted to the world's best double beta decay experiment. This is a detector, and inside we can put a balloon inside to load the double beta decay isotopes, either xenon-136 or tellurium-113. In this case, the total mass of the isotopes is roughly 50 to 100 tons, because this is 20 kilotons. If you load, say, 1%, it's a huge number already. Comparing to all the other experiments and the planning, you see that we're roughly order or maybe 2 orders of magnitude bigger than this experiment. So by the time 2030, we believe that we can do the world's best experiment on neutrinoless double beta decays. So in summary, 3 main portals for new physics, hadrons, neutrons, neutrinos, and Higgs, are all very promising. They were successful in the past, and if we are able to succeed in China to build a Higgs factory, we can be a leader also in the Higgs sector. Otherwise, we will join FCC in Europe to be a major partner. But we are not going to stop there, and we already started working on the technologies after CPC and FCC, and we believe they are going to be applicable after 20 years from now. With good strategies for short, medium, and long term, our future is bright, even though very often we meet oppositions, pessimistic views, and also disappointing events. Thank you.
Thank you, Fang. Due to time limitation, we may have a couple of questions. Anyone have questions? Okay, great.
Okay.
Thank you, Fang, again. Okay, our next keynote speaker is Professor Andrea Liu, recipient of the 2026 ICBS Marie Curie Medal in Physics. So I'll have a short introduction to Professor Liu. Professor Liu holds a Herbert Professorship of Physics at the University of Pennsylvania and is a member of U.S. National Academy of Sciences. The ICBS committee awarded her the inaugural Marie Curie Physics Medal for pioneering the universal jamming paradigm, a landmark theoretical framework that unifies glass, granular media, chlorine, and biological tissues to explain how amorphous systems develop mechanical rigidity without a crystalline symmetry. Before her work, the field lacked a unified theory describing flow, deformation, and relaxation in disordered material. She identified universal structure and dynamic signatures of the jamming critical point and integrated machine learning of soft parameters to decoding localized flow defects governing amorphous solid mechanics, fundamentally rewriting our understanding of glass physics and complex soft matter. Beyond the inert condensed system, she extended her theory to microbiology, revealing how collective mechanical interactions shape cellular and tissue function while building novel crosslink between soft matter physics and neuromorphic computing. Her seminal theoretical breakthroughs have earned her numerous prestigious global honors, most notably the 2025 APS Leo Kantorf Prize, the top international award for statistical and nonlinear physics. Her elegant simplification of the chaotic many-body problems has opened a vast new research avenue for both theorists and experimentalists worldwide. Okay, welcome, Professor Liu.
Thank you. Thank you so much. I completely forgot the title that I had provided, so I'm sorry, there's a new title, but it's the same topic, I promise you. So I'm going to start this out with the story of 3 Nobel Prizes. All basically involving what's happening here? Hello? Okay, I use this one. All involving the same model. Let's see. I'm sorry, just a minute. Where's the... Okay. All right, I'll just use this. Okay. So and I'm going to start this out with the story of the Ising model. Okay. So the Ising model, right, is a model where you have magnetic spins, SI, SJ. They can point up or down. Okay. And they interact with each other with this interaction, the coupling constant J. Okay, and it involves the interaction of 2 spins, I and J, with an interaction between them. So the first Nobel went to Ken Wilson, and among many things, his renormalization group served as a way of understanding the phase transitions of systems where all the J's, Jij's, they're all of the same sign or 0. If they're all positive and 0, if they're all negative and 0, okay, then these things have phase transitions, right? And the renormalization group then explained that why different systems that look completely different, like liquid vapor systems or magnets, actually look the same when you look at their phase transitions. Okay, but of course, the insights from Wilson's prize, right, and Wilson's work went way beyond the Ising model. It covered many, many, many different systems, and really gave us a unifying framework for how to think about phase transitions, okay, and phases. The second Nobel involving the Ising model went to Giorgio Parisi. in 2021, okay? And what he did was, what if the JIJs are not all of the same sign, but they're random, okay? Then you can get what are called spin glasses. The behavior is much more complicated than if they're all of the same sign, okay? And he came up with theoretical ways of handling those systems in high dimensions. And of course, while he started with systems that look somewhat like this, okay, his ideas go way beyond these systems to many, many other systems, including glasses. And that was the basis of him getting the 2021 Nobel. Okay. The 2024 Nobel went to John Hopfield and Geoffrey Hinton. And the innovation, which Hopfield's work came earlier in 1982, okay, his innovation was to say, let me take this and now let the JIJs be individually adjustable. I'm going to adjust them. I'm going to tune them to get behavior that I'm interested in, okay? And that was really a huge change. This work, of course, won the Nobel because it spawned the field of neural networks that led to AI. It also spawned a new field of theoretical neuroscience. And that was quite a lot for the Nobel, okay? But one of the things I like to argue is that it goes well beyond those examples. The tunable matter is really all around us, all in us, in fact, and that is that is so his work really really started a new class of matter. Why do I call it a new class of matter? It's because it's fundamentally different from ordinary matter. So what is matter, right? Matter is collections of a large number of atoms or molecules, or could be grains of sand, it could be bubbles, it doesn't matter. But a collection, it could be people, okay, interacting, large numbers of components, and the collective properties of them, okay? And the famous motto of condensed matter physics was due to yet another Nobelist, Phil Anderson, who said more is different. And the point of more is different, right, is that if you just look at a few objects or a few atoms or a few molecules together, okay, you think you know everything about them, okay? But if you put a lot of them together, you get totally unexpected phenomena. For example, phases and phase transitions, okay? But many other things. So that's the idea of more is different. But the fact is that almost all the matter that has been studied for the last 100 years, the condensed matter, okay, is not, if I look at 1,000 atoms or 10,000 atoms or 10 to the 23 atoms, okay, doesn't make much difference. They look about the same, okay? And that's why, when we teach the Ising model, for example, we often have students do simulations of 100 spins. It's enough. You see, actually, all the hallmarks of phase transitions. So many more is nearly the same as more for ordinary matter, okay? That's not true for the Hopfield model. Once I make my JIJs tunable, okay, what I'm going to call tunable matter, where they can adjust individually, okay, then many more is more different from more, okay? So, or what I like to, another way to say it is bigger is better, right? That's the motto of AI. Bigger is better. You want to make your AI models bigger and bigger so that they can do more and more things, okay? That's completely different from ordinary condensed matter, okay? Or in brains, it's the same thing. Yesterday, I gave the example, if I take C. elegans, nematodes, they have 302 neurons. They can do a lot, okay? But now if I look at honeybees, they have about 1 million neurons. They can do a lot more than C. elegans. Then I take humans with 100 billion neurons, and we can do more than honeybees. Our brains can do more than honeybees, right? So the bigger is definitely better. Bigger is more intelligent, and that's what's driving the huge growth of AI and investment in data centers and all that. It's this property. So this is a really different kind of matter than we're used to. Okay. Another example that I gave is as we have an organism that's starting with a single cell and then developing into an organism. As the embryo gets bigger, okay, it can undergo more and more complex changes, okay, and that's how you end up with an organism, okay? So that's another example of bigger is better, or many more is more different. Okay, so what am I talking about when I say interactions are tunable? Okay, you say interactions or interaction potentials, they're just given to us by physics or chemistry, okay? We can't mess with those, okay? So really, when we're talking about individually adjustable interactions, we're talking about effective interactions, okay? Effective interactions that are characterized by what I'm going to call tunable degrees of freedom. Okay, so they're interactions at some scale. What do I mean? Well, when Hopfield came up with the Hopfield model, his spins represented neurons, okay? And the JIJs, these couplings, represented synapses, okay? So these are not, elementary objects with interactions, or not, according to Yifang, those are not elementary objects, but they're not atoms or molecules that with clear interactions. They are really complex objects, okay? And they have effective interactions when I'm looking at them on some length scale. And then you say, well, why bother to think this way? Why have to go to some scale, look at where interactions are individually adjustable? And the reason why, we know from AI, right? Because if we do that, we can get very, very complex behavior, okay? We know that from AI, and we know that from brains, that making the interactions tunable gives me very complex behavior. So how does that work in AI? Suppose I have a neural network, okay? And I want to tell the difference between cats and dogs. I don't know why people always use this example. So the idea is I have pixels of an image, and I feed them in as inputs here, okay? And then I have outputs that are going to say, is it a cat or is it a dog, okay? So the network has lots of parameters in it, okay, that I'm going to call tunable degrees of freedom, that we're going to adjust to give the output that we want, okay? And how do we train this neural network? We introduce a cost function, which compares the output that we get, which I'm going to call the free output, okay? In other words, I put in the inputs, I just grind through the networks, the outputs are just going to be free to be what they are, okay? That's the free output. I'm going to compare that to the output that I want, okay? I don't know which is bigger, so I'm going to square this so that when I minimize it, I want to bring this to 0. If this is 0, then the output that I get is the same as what I want, okay? And I do this for each training example, okay? That's the number of turns of the sum is the number of outputs times the number of training examples. All right, so that's the idea. You minimize this cost function. And AI has taught us some really important lessons, okay, that we're going to take to heart, which is what? First of all, this works really well, okay? Secondly, the solutions don't have to be optimal. I don't actually have to reach 0, right? The goal is to reach 0, but you're pretty happy if even if it doesn't reach 0. And this is important because people used to get all worked up about, is this the lowest possible value of the cost, or is it just some low value, okay? And to prove that it's the lowest possible value is very, very difficult, okay? But just to say, it's low enough, that's pretty easy, okay? So that's one of the things that we've learned from AI, that we don't have to care whether it is actually the best, the lowest possible value of the cost. It just has to be low enough. The other thing that we've learned is that actually having more parameters, okay, then we have terms in this sum. So each term in this sum says, I want the free output to be the same as the desired output. That's what each term in this sum says, right? And that's a constraint. I'm placing a constraint on this system. And so the number of terms in this sum is the number of constraints. And what we've learned from AI is that we want more parameters than we have constraints. And this goes against everything we learned, right? So when we start learning algebra, 2 equations, 2 unknowns, okay? You don't want more equations than you have unknowns, okay? Then you don't have any solutions. If you have fewer equations and you have unknowns, then you have lots of possible solutions. That's usually not a good thing. Here in AI, that's a really good thing, okay? That's the regime that you actually want to be in, okay? So why is that? So I'm going to now imagine, think about the cost function, okay, in a very, very high dimensional space where along each axis is all the values, all the possible values of my first tunable parameter. Then on the next axis, all the values of the next tunable parameter, and third axis, right? So I have all these orthogonal axes, one for each tunable parameter. This phase space, I can think of the cost function in this phase space, okay? And I want to bring it down to 0, okay? Or bring it to be very low. And this blue area, so here my phase space is 2-dimensional, right? But for something like ChatGPT, okay, it's a trillion dimensional, okay? But I'm drawing here in 2 dimensions. And now I'm lowering the cost, okay? And the cost, this blue part is where the cost is low enough for us to be happy. These are good enough solutions. The white is where it's not good enough, okay? And the point is that in this regime, it's very easy to start somewhere, okay, and end up in this blue region. I started out with random parameters, and now I go downhill in the cost, and I easily end up in this blue region, okay? Also, there are many good solutions. So I'm sitting here, and now I change some of my parameters. I'm still happy. It's fine. It's not a problem, okay? And this is the important thing for generalization, okay? Right away, oh, by the way, this is what over parameterization, right? It's the number of constraints divided by the number of tunable degrees of freedom. We want this to be small. And you see right away from this ratio, okay, why many more is more different, right? Because if I increase the size of the system, if I increase the number of tunable degrees of freedom, I can increase the number of constraints. So I can get more complex behavior. Okay, and still be in the regime where this is small. Okay, so the more degrees of freedom I have, the more constraints I can satisfy, and the more complex my behavior can get. All right, so how do we solve neural networks? We use variants of gradient descent, just ways of going downhill. Okay, and you think, hey, going downhill is easy. Okay, we do that when we're skiing, right? We're going downhill. But there we're going downhill in 2 dimensions. We're adjusting our latitude and longitude, right, as we go downhill. But imagine skiing in 1 trillion dimensions, okay? That actually takes a lot of calculation, a lot of computation. And I had to calculate what is the direction of going downhill. And then I had to be able to go in there and modify all my tunable degrees of freedom in the right direction, the way the gradient descent tells me to do it, right? And that's fine if you're doing it on the computer. It's not a problem. But again, that requires more computation, okay? So design by minimizing a cost function with a gradient descent kind of method, okay, is inherently a global thing. and it requires a processor. It requires a huge amount of processing, and we're running into problems right now. And so this led us to think, okay, can tunable degrees of freedom be adjusted, okay, to get a collector response that you want without a processor? Okay. And actually, that's what Hopfield and Hinton both did. Okay. That's not a very well recognized part of their Nobel Prize, but they had what are called, they introduced local rules for how to tune these coupling constants. Okay. What did Hopfield do? He said, I'm going to change my couplings, okay, following what's called the Hebbian rule. And this is a rule that, you know, there is a lot of, this is a rule that is seen in the brain, okay? The neurons that fire together wire together, okay? So he said, okay, spins that are pointing in the same direction are firing together, okay? And they're gonna wire together. That's gonna determine what their coupling is going to be, okay? And with that, he found that the Ising model, with that local rule, the Ising model could store memories. If I give it spin configurations that's a little bit like a stored memory, then it can find that memory. It can retrieve that memory, okay? Hinton came along then 20 years later, okay, and came up with, for the very same model, for the Ising model, okay, he suggested a different rule. It's called contrastive divergence. I'm not going to go into it. But what did that do? That gave the Boltzmann machine. And what that does is it does unsupervised learning. It learns probability distributions, okay? And it can generate from examples drawn from a probability distribution, it can generate new examples from that distribution. So it can do what's called generative tasks, okay? So unsupervised learning and generative tasks. So the same model, okay, but with a different local rule for tuning the couplings gives me totally different function, okay? Hopfield, one rule gives me associative memory. The other rule gives me unsupervised learning and generative tasks, okay? So what's so great about local rules? Well, you might have noticed, but your brain is actually not connected to a computer. It's able to learn, but it's not connected to a processor. It is the processor, right? So what's the difference? The AI network needs a processor. The brain follows a local rule, for example, the neurons that fire together wire together, okay? It doesn't need an external processor to do it. It just learns it, okay? That difference by updating by a local rule versus doing gradient descent on a processor, okay, makes the difference between the tiny amount of energy our brains use and the amount of energy that AI requires. So a single AI chip in a training cluster uses 600 watts of energy, okay? How much does your brain use in an entire day? Well, it's a lot actually it's about a quarter of the food we eat, okay? That we take in. That's a lot of energy for, you know, a lot of the energy that we take in goes into the brain, okay? But 2,000 kilojoules per day is only 20 watts, okay? So our brains are running on 20 watts. They're doing much more than physics, okay? They are, of course, controlling our heartbeat. They're, you know, and our breathing, all the things that keep us alive. And they're allowing us to walk and talk, okay? As well as learn things, as well as learn physics, okay? So that's a lot, doing a lot for 20 watts compared to one AI chip in a training cluster using 600 watts, okay? Why, yeah, and a typical large language model training cluster, by the way, has 100,000 chips in it. It really chews up a huge amount of energy, okay? So what's the difference, Okay, why is this? Part of it is that digital is expensive because it gives you precision, but it is also expensive. Analog is a lot cheaper in energy. But the main difference is what's called the von Neumann bottleneck, okay? So what is that? The von Neumann architecture for computing is that I store data in memory, okay? And then I do operations on it. I do things with it in the processor. And every time I need to do something, I need to take data, move it to the processor, do my operation, bring it back to memory. So I'm constantly shuttling data between the memory and the processor. And they are physically in different places, okay? In the brain, okay, where is the memory of the tuned parameters held? It's held in the synapses. It's the memory of what are the values, what are the synapses, is in the synapses physically themselves. And the synapses are what are also doing the computing, okay? And this is what is called in-memory compute. That physically, where the memory is, it's in the object that is actually doing the computing. It's also in the object that is doing the learning. That when I build a synapse, okay, I have now a synapse there. The fact that I have a synapse there is just there in the existence of that synapse. It's not stored somewhere else in some memory, okay? It's stored in the object itself. And that's called in-memory learning, okay? And that is what leads to this huge energy savings of the brain compared to AI. Okay, so what this led us to were systems, okay, that don't try to copy the brain. There's a field of neuromorphic engineering started by Carver and Mead, okay, in the 1980s, where people build circuits, electronic circuits, okay, that mimic the brain, that they use subthreshold transistors, they spike, and then transistors that spike together, wire together, okay, they're really trying to copy the brain. What we wanted to do was to say, could we do this without copying the brain, okay? Could we get some of these wonderful brain-like advantages without copying the brain, okay? And so that's the idea of what we're doing. Our first generation is just electrical networks of resistors, okay? Resistor networks. You learned this in E&M as in introductory physics, networks of resistors. What's different about our resistors is that they adjust their resistances, okay, according to a local rule, okay? And the local rule is such that when they adjust their resistances, they can do supervised learning, okay? So I'm going to explain how that works. So the idea is you put on your inputs as voltages, and then your desired outputs are voltages on other nodes of your network, okay? And then the question is, so suppose my inputs are here and here, okay? And I want to adjust the voltage on this output node over here. Then the question is, each of these blue lines is an adjustable resistor, okay? What should the resistances of all of these be so that given these two inputs, I get the output voltage here that I want, okay? That's what we asked, okay? And that local rule then is what we use. And the nice thing about this, okay, well, let me just explain how the rule works. Okay, so that let's just talk about that first generation. So what was the idea? And this was really the idea of a brilliant postdoc, Naki Stern, who's now a PI at AMOF in Amsterdam. Okay, so what's the idea? Suppose I put on voltages here, input voltages, some input voltage, let's just say an input voltage drop across these two nodes, okay? And I have, you know, here some output nodes, and I want some desired voltage drop across these two nodes. Just very simple, okay? And then the question is, what should the resistances be in this network? Okay, what should all these resistor values be in order to get the desired voltage? Okay, so we usually start with a cost function, right? As I told you, you say, all right, I'm going to apply the inputs. Okay, I'm going to apply these, and I'm going to look at the response over here that I get. Okay, that's the free response. I just apply the inputs, and I leave the target free, the output free, and I look at the response, and I compare it to what I want, right? I don't know which is bigger, so I'm going to square it, and then I want to minimize this. That's what we would ordinarily do, okay, to train our network. Instead of doing this, okay, we're going to do something slightly different. We're going to say, let's apply the source. Let's leave the target free, okay? That's what I'm going to call the free boundary condition. But then, okay, how do I tell the network what I want the target to be? I'm going to apply the source, and I'm going to apply the target response that I want. Okay, so I can apply voltages here, which are the ones that I want. Okay, now here's the beautiful thing. I'm going to call this the clamp state. This is where I show it the label. Okay, the power in the clamp state has to be greater than or equal to the power in the free state. Why? That's because of Kirchhoff's law. Kirchhoff's law says, because of charge conservation, there's no net current at every node. That's equivalent to minimizing the power. Okay, so the power is minimized. Physics says the power has to be minimized. That means that if I take off these inputs here at these, if I take off these applied voltages, the system's going to go right back to this. That means the power here has to be greater than or equal to the power there. Okay? What's great about that? I don't have to square it. You hear? I didn't know which one is bigger, so I had to square it to make it positive. So I minimize it, I bring to 0. This, I know it can't be negative, so now I can just minimize it without squaring it. And if you minimize it, okay, so I say, all right, the conductance of each edge, I'm just going to go downhill by taking the derivative with respect to the conductance of this difference in the power, okay? But the power, right, is just the sum over every edge of the voltage drop across that edge times the square times the conductance. You work that out. The rule becomes that the way I change the conductance on edge I depends on the voltage drop across that edge in the clamp state squared minus the voltage drop across that edge in the free state. Why is that so great? Okay, this is, I'm not going to go through the math, this is a local rule. In other words, I update the conductance on this edge. I only need to know the voltage drop across that edge. I don't need to know the voltage drop across any other edge. That's all I need to know. What's so great about that? How can that lead to collectively doing supervised learning? It's because due to Kirchhoff's law, the voltage drop across this edge depends on the voltage drops on all the other edges. But I don't need to know what they are. This is all I need to know to update. Okay? So this is great, right? But there's a problem. This is a physical system. If in AI, I just introduce a cost function, okay, and I minimize it, and I'm done, okay? So here, we've placed gradient descent on the cost function with this local rule that takes us downhill, that effectively does gradient descent, and then we adjust our tunable degrees of freedom. We should be done, right? But no. This is a physical system. It has to obey physical laws, okay? And because of that, okay, that physics says, no, you have to minimize the power, okay? Every time I change the conductance on an edge, I'm raising the power, okay? I'm changing everything, and I have to adjust the voltages on the nodes to get Kirchhoff's law back again, okay? Physics says I have to. So every time I change my conductances, my tunable degrees of freedom, according to my local rule, I have to go back and minimize the power with respect to the voltages of the nodes, the node voltages. So it's really a double optimization problem. okay? Because it's a physical system. Because it was a physical system, I was able to come up with a local rule. But I pay a price. I have to do 2 optimizations instead of 1. And this makes it a terrible computer algorithm, okay? It makes it really slow because even though I don't have to do backpropagation, I still have to do this minimization, okay? So Naki and I were working on the paper. It was during the pandemic. We were at home, stuck at home, okay? And I was thinking about this, like, this is no good as a computer algorithm, so what's it good for, okay? And then I realized the key is to do this, okay, in real life, in the lab. Why? So I've gotten rid of this gradient descent by doing the local rule, but I still have to minimize the power. That's still global. It still requires a processor, okay? But if I do it in the lab, I put on input voltages. Physics just satisfies Kirchhoff's law and gives me the output voltages automatically. I don't have to do anything. Physics does this for me, okay? But like, oh my God, but how can we do this? I had no idea of how we could possibly implement this local rule, okay? Physics says this, no need to worry about this, but how do we actually implement the local rule in a physical system? So I was talking to my husband about this because we were locked down at home. My husband is Doug Durian is a soft matter experimentalist. He was working on granular materials and foams. And I said, you know, we got this problem. We got this great local rule, but it has to be done in the lab. I have no idea. And he sort of listened. He's a quiet guy. Okay, he listened. He didn't say much. And he went away. It's like, okay, you know, I vented to him, fine. A week later, he came back and said, I think I know how to do it. Okay? And so we hired a postdoc, and he came and he did it. Okay? And it just blew us away. It actually worked. Okay? So Sam Delavu, this brilliant postdoc that we hired, actually figured out how to implement this. So Doug's trick was, what is the problem? You can't run 2 different boundary conditions, free and clamp, okay, on the same system at the same time. So how are you going to do this? So the solution that Doug came up with is to build 2 networks, identical twins, one with the free condition, the other with the clamp, okay? But the point is that it works. So how am I doing on time? Have I reached my time? Am I getting close? Anyway, okay. So I just want to, this is such a cool thing. So you have one node that's ground, okay? And then it's a classic problem in computer science, very old problem. You have 3 different kinds of irises, 3 different species. And you give them 4 numbers, the lengths and widths of the petals and the sepals, okay? These 4 numbers. We convert these lengths, okay, into voltages. So we need to input 4 numbers. So we choose 4 nodes, 1 for each of these quantities, okay? And then the key is to sort the irises out. So some poor guy measured 50 irises for each species. He measured these 4 numbers, okay? And the question is, given these 4 numbers, can you identify the right species? So I have 3 species. I need 3 output nodes, okay? So that's all you give it. And then we give it, out of the 50 flowers of each species, we give them 10 to train, and we test on the remaining 40, okay? And we get a classification accuracy of 95 to 97%, which is what you can do as well as you can do with a linear classifier on the computer, okay? This is a linear system, linear resistors, therefore it can only do linear classification, but it does as well as something on the computer. The second generation is nonlinear, okay? I want to highlight my brilliant colleague, Mark Miskin, in the electrical engineering department at Penn, who came up with the initial design. Sam Delavu was the one who worked this all out again. And now we have 32 edges. The first thing had only 16 edges, 9 nodes. This has, 16 edges, 16 nodes, 32 edges. Now it's nonlinear, and it can do nonlinear classification regression This is curve fitting. This is just doing a curve fitting to these points. Okay, and you can see the system, fit that curve. Okay, all right. So the great thing is we can rip out these edges and it can still learn the task because it's over parameterized. It's very robust to damage, so it's manufacturable. In fact, Sam said these networks are hell to debug, okay, because they keep working. So, he put the inputs here, outputs there, it would work. He put the inputs here, outputs somewhere else, they would work. Then he changed where he put the inputs and outputs, and suddenly it wouldn't work. And it turned out all along there was one of the edges was defective, okay? It was a defective edge, but the system just learned around it unless the placement was such that it just really couldn't learn around it. So it's extremely robust, that's good. That means it's manufacturable. All the changes of the conductances or nonlinear conductances are calculated in parallel at every edge at all the time, okay? And this version, okay, built on breadboards, terrible, okay, already is only using 10 times more energy per parameter to do an already trained task compared to the state-of-the-art energy efficient AI chips. Okay, it's only using 10 times more energy. And what this is a huge system on breadboards. You scale it down to a chip, you should get orders of magnitude better energy. Okay, so this is all great from a technological point of view. We're excited about it. Okay, but why do we care as physicists? The reason why is because the second generation, even with 16 nodes and 32 edges, okay, this system is already 30 times faster than doing it on the computer, okay? Solving the same thing on the computer. That's because doing the power, or it's not power, but the generalization of power when you have nonlinear resistors is very time consuming, okay? So if we really want to scale up, which is what we want to do, of course, so that these systems can do more and more complex things, we had to scale up in the circuits, not on the computer. We can get much, much bigger, and that's how we can really study this kind of matter, this tunable matter system, is experimentally, where it has a huge advantage over simulations. Okay, so I just want to point out that the brain, of course, yesterday I talked about the actin cortex of a cell. There are many, a developing embryo, all of these systems I can think of. There are many systems that we've been thinking about, allosteric proteins, which have the property that they do in-memory computation and in-memory learning. And I think one of my speculations is, biology, of course, all of biology operates at much, much lower power than AI, okay? And maybe this is an important reason why, okay? But I just want to end by saying, this is really tunable matter, I think is an incredibly exciting form of matter. It has challenges that we need to face up to, okay? That we haven't confronted so much as condensed matter physicists. And we're going to need new frameworks, theoretical frameworks, new computational methods and studies, and new experimental systems that we can study and experimental methods to study to confront this new class of materials. So I think this is a very exciting challenge for the future. So thank you.
Thank Professor Liu for this cool talk. So we have time for a couple of questions. And anyone have questions? Okay, our audience is so quiet.
Okay.
Thank
No
you.
questions.
Thank you again. So our last speaker is Professor Xiaogang Wen, recipient of the 2026 ICPS David Gross Medal in Physics. So let me introduce Professor Xiaogang Wen. He served as the CISA and the IDA Green, professor of physics at MIT, and is a member of the U.S. National Academy of Sciences. He's honored with the inaugural David Gross Physics Medal for inventing the revolutionary theory of topological order, which offended the Landau's century-old symmetry breaking paradigm as the sole classification standard for quantum phase of matter. Professor Wen proved that a strongly correlated quantum material holds the exotic quantum states governed by long-range quantum entanglement, independent of symmetry breaking. He established the foundational frameworks for non-abelian topological order, symmetry-protected topological phases, and string net condensation, demonstrating that fundamental gauge theory and elementary particle can emerge purely from entangled quantum bits. His mathematical language bridges condensed matter many-body theory, high-energy quantum field theory, particle theory, cohomology, and quantum information science, and forms the core theoretical foundation for fault-tolerant topological quantum computing. A recipient of the ICTP Dirac Medal and APS Oliver Barclay Prize, he has forged an unprecedented unified framework connecting microscopic quantum entanglement to the fundamental laws of nature. Welcome, Professor Wen.
Okay, you just heard about this talk about elementary particle and the fundamental force in the first talk tonight. And then you'll hear about this atomic matter. And my talk is about quantum matter and its connection with elementary particle and the fundamental force. So, our world is very rich and complex, and we're kind of wondering how to understand this rich and complex world. And then certainly there's an issue, what do you mean by understand? And, physics develop in cycles. First we discover a lot of phenomena, and then we try to understand them and try to unify those phenomena using some simple theories. And then we have a more discovery and we need more unifications. So each big unification is kind of like a revolution in physics. And so those unifications brought us into some new world. And there's a new fundamental concept was introduced. And there's new mathematics was introduced. That's a sign of new understanding and a new unification. And maybe the first unification, a big one, is a mechanical unification. It's to unify the falling apple on the earth and the planet motion in the sky. And the new world view is that all the matter are formed by particles, and those particles follow some kind of Newton's law. And the new mathematics introduced at that time is calculus. Before calculus was introduced, we don't know how to describe curved motion, so we had to introduce calculus to describe this new phenomena of a curved motion. And another revolution, I would say, is the electromagnetic revolution, which unifies seemingly very different phenomena like electricity, magnetism, and the lights. And the worldview here, I will say that discover a new form of matter, where it's not just a particle. There's a new form of matter. It's kind of waves. There's a wave-like matters, which all be very different law. So the wave-like matter all be the Maxwell equation. And the new mathematics maybe is a differential equation of fiber bundle. Then we have this relativity revolution, which unified the space and the time, and also unified the force as a deformation for space-time. So actually, it's a discovery of a second wave-like matter, which is a gravitational waves. And the new mathematics here is a Riemann geometry. Then the fourth revolution, I would say the quantum revolution. This is the most reluctant revolution. It means the theories are driven by experimentalists and get crazy about this. It's just very uncomfortable, but that's the truth. So what is unified is unified like there's a hydrogen spectrum or some other atomic spectrum, and there's a double slit interference, and also this black body radiation. Again, very, very different phenomena which are unified under the single theory. And the new world view is very interesting. And the particle-like matter and the wave-like matter are unified. The actual matter is neither particle nor wave, and both particle and wave. So it's some kind of incomprehensible existence. But that's a real existence. Both particle and wave are not existence, and this kind of dual things are real existence. And the new mathematics is a linear algebra with a tensor product. So here, if you're truly brainwashed by quantum mechanics, you will arrive the following conclusion. So we used to think the information and the matter are two very different things. The information are property carried by the matter or attribute of a matter. But however, we know that the change is a property of information. So the frequency actually is a property of information. However, according to quantum mechanics, the frequency is energy scaled by the h bar, is a Planck constant. And according to relativity, energy is a mass. But the mass and energy are property of matters. So quantum theory really tells us frequency and the matter is the same thing, but the frequency is purely a property of information. So that really suggests that the information and the matter are same thing. So that's if you're truly brainwashed by quantum theory, the information matter should be unified. Okay. And so let's try to persuade this idea, how the information and the matter is really the same thing. We used to think, one idea, or maybe one philosophy to understand universe is this reductionism, which we view matter as a player on the empty stage, which is a vacuum. So vacuum is a stage, and the matter is like an actor on the stage. They do things. They make a performance, or opera, whatever. But however, there's another philosophy, emergentism, which actually unify the actor and the stage. They say they are the same thing. So we only have a stage. And so here we assume that the space itself is a dynamical medium on the ocean of qubits. That's where information comes from. Qubits is an elementary building block of information. Okay, so here is the picture of qubits. So we imagine the vacuum actually is an ocean of qubits, and then the matter or this elementary particle are just a kind of bubble or whirlpool or what type of deformation of those qubits. Okay, this kind of echo this the ancient Chinese philosophy that everything comes from Taiji. Taiji have two states, which is Liang Yi. So actually, Taiji is a qubit. Liang Yi is a two state of single qubits. And 四象 means 2 qubits, 八卦 means 3 qubits, and our universe is about 10 to the 120 qubits. So it's go much beyond 八卦. And so then the issue is that whether this kind of qubits ocean point of view can really explain fundamental particle or elementary force or not. Then we look at our world. The elementary particle and fundamental force in our universe, like Yifang Wang talked about, is very, very complex, very rich. For example, they talk about the infinity, like Qing Tong Yao mentioned about our universe have infinity mysteries, and now I only talk about the 8 of infinity mystery. So there's 8 mystery here. And so this 8 mystery was used as a building block of a standard model in elementary particle physics. So we have these identical particles. So like all the electrons in different places are really identical. And we do have a wave satisfy Maxwell equation, which we call light. And we have a wave satisfy Yang-Mills equation, which is a strong and weak interaction. And we have a particle with a Fermi statistics satisfy Dirac equation, which is an electron and a quarks. And those fermions actually have a fractional angular momentum, which is a very, very strange thing. And we have Lorentz symmetry. And there's more details in only right-hand or maybe left-hand fermion coupled to SU2 Yang-Mills waves. And we also have wave satisfy Einstein equation. So those are very fundamental property and of a matter. And then the question is that whether those elementary properties or mysteries can come from the qubits. The qubits really, really simple, just 2 states. They kind of bosonic. Okay. So one very idea for simple qubits ocean is that so like a 0, if qubit is equal to 0, it's empty space. The vacuum means qubit 0. If some qubits become 1, then that's a particle. So here we have 2 particles. There are 2 qubits equal to 1, and the rest are 0. That's 2 particles. And so then if you're using this idea, how much mystery we can explain? Well, these 2 particles actually is identical particle. So actually it's amazing. This qubits idea naturally gave rise to identical particle. I remember when I learned quantum mechanics, the identical particle notion is very hard to swallow. If you have this reductionism point of view, the vacuum is empty stage, and the particle player on the stage, it's very hard to understand why we have identical particle in this kind of setup. But in this qubit medium setup, identical particle is unavoidable. We always have identical particle. But however, except identical particle, we don't get the rest almost. So we only get almost 1 mystery out of 8. Okay. So actually, so the big question is that whether there's some other qubits ocean which produces 8 mysteries. Yeah, that's became a key question. Okay. 150 years ago, when Maxwell proposed his Maxwell equation, he had been thinking about what kind of media support this kind of equation. And actually, in his paper, he have this big gear, small gear models. This idea is that when the big gear rotates like the curve of magnetic field, and the center mass motion of small gear may move, that's like a currents. So this big gear and small gear may produce Maxwell equation in some way. And actually, I don't know why the hexagonal gear can turn, but one can overlook these technical details. And so nowadays, we really try to follow this Maxwell's original idea to see if you quantize those gears, this quantum gear model. Nowadays, we got quantum rotor model, where the quantum rotor model can produce this 8 wonder of a universe. So one idea of this we can try is that instead of assume zero as our vacuum, we assume some kind of gas, some mixture of 0 and 1 is our vacuum. So this is the particle is 1 qubits, and the between particle is 0 qubits. And then we may have this 1 qubits may form a random superposition. That's what we call quantum fluid, quantum liquid. And the quantum liquid particle, quantum liquid of 1 qubits, well, this will be the proper medias. So actually, indeed, if you do this quantum liquid of 1 qubits, indeed you have waves. And this wave has a linear dispersion relation, just like a light wave. So in some sense, we get something very close to light wave. Except that this kind of wave satisfies Euler equation, not the Maxwell equation. So this kind of wave is only one polarization. Light wave have 2 polarization, so we are close but not quite there. Okay. So then we can consider another ideas. So maybe this 1 qubit form a crystal. And we have a crystal, and then we can see the crystal can deform in 3 ways. There are 2 ways to do the shear deformation, and the third way is to do density compression deformation. So the crystal indeed also gave us a wave with a linear dispersion relation, just like a light wave. But here we got 3 polarization. Okay, it's still missing. It's still does not agree with the Maxwell equation. So actually, the crystal wave is have this kind of elastic equation. It's not the Maxwell equation, but something close. So in some sense, I try to say the condensed matter physics is an engineer of wave equation. The condensed matter physics try to study all kind of order, all kind of organization of matters. And the different organization led to different wave equation. We got the Euler equation, we got the elastic equation. Then we really ask, do we have some kind of another organization which gave us a Maxwell equation? Okay. And unfortunately, after Maxwell equation for 150 years, we tried all kind of organization, like using symmetry breaking, order parameter, and none of them gave us a Maxwell equation. And so it's really very frustrating. And so what do we do? We declare Maxwell equation and the light is a fundamental. So don't ask, that's a standard answer. But however, if you ignore what the teacher says, you're still thinking, I should ask. And keep this puzzle in your mind all your careers. Maybe some days you may have some ideas. Okay. So actually, there's a new insight come from totally different place, there's a quantum Hall effect. Quantum Hall effect really gave us a new kind of matter which is beyond the symmetry breaking, beyond order parameter description. There, the major player is a long-range entanglement, which we call topology order. Actually, I regret I introduced the name topology order because I should call entanglement order. But this word was introduced in 1989, where at that time, the quantum information entanglement is not popular words. It became popular in maybe around 1995, And I think the qubits is introduced after 89, or maybe around 1901. So at that time, as a physicist, we are not thinking about entanglement. We think about topology, but what really new is mainly about the entanglement. Okay. So what really happens that these 2 examples, like this crystal order, is a pattern for 0 and 1. It's a product states, not the entangled states. And this kind of quantum liquid may be entangled. No, it's not entangled, because on every physical site, we have a superposition with 0 and 1. And that means that this superposition is a spin x direction. We have a product state of a spin x direction, and still product states. So actually, for some reason, for past 17 years, we think about all kinds of unentangled states, and we think that's our universe. Actually, it's not. Actually, there's another universe which is highly entangled states, which actually is which is the quantum Hall state really force us to think about the highly entangled states. And one way to get the highly entangled state is to get a superposition for 0 and 1, but not arbitrary superposition. And only superposition of some configuration for 0, 1 means like superposition of 1 which form a string, So actually this string liquid is an example of a highly entangled states. So this really led us to think about the string liquid. If this one qubit form a string, and the string form a liquid states, what happens? What is density wave in the string liquid? It turns out that the density wave in the string liquid happen to be the wave that satisfy Maxwell equation. And the reason is following. Because it's a string, it's always from a closed loop. Therefore, string density cannot change in the direction of a string. The string density can only change in the direction perpendicular to the string. So that's precisely and also string density is a vector field, not scalar field, because string have orientations. In some region, we have more string, but you say more string in which direction? So more string density is a vector field. And where string density can only change perpendicular string means the string density vector field have 0 divergence. That's exactly the equation for the electric field. So actually electric field is a string density. Then you ask, what is a natural equation for this vector string density to evolve and maintain its divergenceless property? Then you can just make a guess, Maxwell equation. Maxwell equation is a simplest equation for the divergenceless vector field to evolve. So from this point of view, the string density Maxwell equation just come out very, very naturally. After we realize this, I just wonder why it takes 150 years to realize this. We should know this long before. Okay. And then this idea can be generalized. We can even get the Yang-Mills equation. If you assume string can branch, and then not just a loop, the string can branch. This kind of so-called form of string net. And the string have different types that have a branch. This branching of a string is actually the fusion rule. I talked about this morning. And the fusion rule can have a group behind the fusion rule. So that's where gauge group is come from this branching rule. Okay. So if you do this branched string net liquid, this mathematics is more sophisticated, but you'll get a Yang-Mills equation from this branched from string net liquid. And also category theory coming from here as well. And we can even obtain Fermi statistics. When I mentioned that, we say the string density wave is a gauge field. So what about the charge? What about the electron, the gauge charge? Actually, end of string is gauge charge. Because end of string is divergence of string density. We know divergence string density, divergence electric field is a charge. But what is more important is really following. This end of string can be bosons, but however, depend on this wave function of string liquid. For another class of wave function string liquid, the end of string can have a Fermi statistics. This is most crucial. So actually, Fermi statistics can emerge very naturally from particular string wave function. Yeah. So therefore, the Fermi statistics do not have to be a fundamental property of nature. It's just a property of qubits, or just a property of entangled qubits. Okay. So therefore, this the gauge interaction, Fermi statistics, Dirac equation, Maxwell equation, Yang-Mills equation, all unified under this string net entanglement. A string net actually describes this a particular type entanglement, and this kind of entangled media would produce a Maxwell equation, Yang-Mills equation, Dirac equation, and so basically that's really led to this idea is that this kind of specially entangled quantum matter can produce 7 of 8 wonders, and we are working very hard on this some kind of entanglement which can produce Einstein equation, and so far we have not been able to produce that, and it's maybe technical or maybe there's something very fundamental. I don't know. Yeah, And so, but at least right now we have the unification, which unified elementary particle, fundamental force, Fermi statistics by what? By qubits, by highly entangled qubits, or maybe say by quantum information. And so as I emphasized this morning, is that this highly entangled qubits, highly entangled degree freedom is a new phenomenon and require category theory or group homology, those kind of modern mathematics to describe it. And so by studying this highly entangled quantum matter, we forced and reluctantly to learn those advanced maths, And I wish there are some easier textbook written for physicists about those abstract maths. We do need them, and we really, really need them. These new maths are really needed to understand this highly physical phenomena. So basically, this space and matter interaction seems can be all unified. So this is a kind of a ultra unification. That's it. Thank you.
Thank you, Professor Wen. So again, we have time for a couple of questions. Yes.
Do you have an analog for the Higgs mechanism?
Yes and no. The Higgs field is let me what I say. The Higgs field is okay. Okay, here I say the energy string carry gauge charge. The energy string can be boson and can be fermions, depending on the wave function. The Higgs field it will carry gauge charge, but it's a bosonic, so it's a kind of bosonic version of energy string. And also there's a fermionic version of energy string. So those kind of these are in detail the model building. But however, related to your question, there's a from elementary particle point of view. Actually, there's a prediction from this qubits ocean. That is, all the composite fermion must carry gauge charge. At the moment, the standard model will contain the composite fermion which are gauge charge neutral. This would contradict with this qubits ocean point of view. The qubits is intrinsically bosonic. It requires fundamental composite fermion to carry gauge charge. So there are certain beyond the standard model have this property that all the composite fermion carry gauge charge. Those are more compatible with the qubits ocean point of view. And the experimental consequence of that, there are additional cosmic string. Addition means more than standard model, so there's maybe additional cosmic string because it's a Z2 gauge theory and things like that. And yeah, so that's maybe the result of this. Yeah.
So you have eight equations, and you have one left, the Einstein equation to generate. So you must be working with, for example, the gravitational wave as the deformation of space and time, and you must trying to find out whether this deformation of space-time has anything to do with the cubic string.
Yeah,
right?
Exactly. So right now, if you assume the qubits ocean, we can produce all kind of waves. Because those waves reflect the space-time structure. We can produce a Maxwell equation, Dirac equation. So we kind of simulate, kind of come closer to our space-time. But however, we do lack of Einstein equation. So our space-time have Einstein equation means that it has some structure which we are unable to simulate using qubits ocean idea. So either imply qubits ocean idea is wrong, we need something else. Or maybe that means it's okay, but we need just another order, another entanglement structure. This is not clear what's going on here. I myself are hopeful that maybe it's just another kind of entanglement, which another unknown entanglement, not string-like entanglement, some other kind of entanglement, which can lead to Einstein equation. So then if that's true, then we can really also say that right now we can claim that the Maxwell equation is a deformation of a many-body entanglement. And we'll try to say whether Einstein equation can also be viewed as a deformation of many-body entanglement or not. So that part we are not so sure, yeah. And so in some sense, that corresponds to the territory of quantum gravity, whether there's an emergence of gravity can be achieved. Or maybe gravity means something deeper than qubits. Certainly that would be even more interesting. You know, the qubits is not answer. Something even deeper than qubits. Then I don't know, because qubits at the moment, the standard formulation quantum mechanics, qubits is the simplest building block for quantum theory. If something deeper than qubits, I just couldn't imagine in quantum theory what can be more elementary than qubits. That would be really, really interesting. And so basically, that almost implies the quantum theory is wrong. We have to really have a new theory beyond the quantum theory. Yeah.
Okay, actually we are significantly behind schedule. Let's thank Xiaogang Wen again, and thank all keynote speakers.
Intensive theoretical reports call for a pause here. We invite you to join the dinner, over which distinguished guests, ladies and gentlemen, welcome back to the venue of the ICBS International Congress of Basic Science 2026 Physics Night. It's our great fortune to gather the world's leading scholars here to discuss fundamental science, promote the spirit, and to the broader public. We have been doing this for 4 years. Every year for Physics Night, we talk about this Congress, the importance of basic science, the future of physics study, from which we got so many inspirations from our leading scholars. And I believe so will we today. Our leading scholars will talk about where will the next breakthroughs in fundamental studies, breakthroughs in fundamental physics, both theoretical and experimental, occur over the next 2 decades. Let's invite them. Our first guest, Professor Shan Jin from Nanjing University. He's head of the Chinese group of the Atlas Collaboration. Welcome. Professor Hiroshi Oguri from California Institute of Technology. He's the member of the American Academy of Arts and Sciences. Welcome. Professor Subir Sarkar from University of Oxford. He's emeritus professor at the University of Oxford. Welcome. Professor Andrew J. Liu from University of Pennsylvania. She's the member of the National Academy of Sciences, member of the American Academy of Arts and Sciences. Welcome. Professor Xiaogang Wen from Massachusetts Institute of Technology. He's member of the National Academy of Sciences, member of the American Academy of Arts and Sciences. Welcome. Professor Yifang Wang from Institute of High Energy Physics, CES. He's member of the CES and the World Academy of Sciences, a foreign member of the National Academy of Sciences of the US, the American Academy of Arts and Sciences, the Royal Society, and the Russia Academy of Sciences. Welcome. Professor Xiang Dongji from T.D. Lee Institute, Shanghai Jiao Tong University. He's Hongwen Chair Professor at the T.D. Lee Institute, Shanghai Jiao Tong University. Professor Xiang Dongji will be holding this panel. Welcome.
Okay, so welcome everybody, and we're gonna have some fun today. So the topic today for the discussion is, what would you predict for the next 20 years, the fundamental breakthroughs in physics, both in theory and experiment? So let me try to understand a little bit about the topic. And I was thinking about why 20 years. I guess the reason for 20 years is long enough that we can hope to have a fundamental breakthrough, but sure enough that every one of us could be here to verify what we said today. So we're going to hold you accountable for what you said today, right? So I think that's a brilliant idea. So we're going to talk about the fundamental breakthroughs. So I think, someone said prediction is very difficult, especially about the future, right? And Niels Bohr, right? Niels Bohr said this, and many other maybe also said that. But I think today we're going to make it even more difficult, because we have 6 brilliant physicists here. And not only we ask you to have a prediction, but I also wanted to have you have a consensus. And so my role here is try to protect different opinions, and to protect the clock, and protect also the audience from unknown terminologies from your own fields. And so let's begin. I think we all understand what the question is. And I would like you to ask you, each of you, 3 minutes, and to explain what do you think the fundamental breakthrough is going to be in the next 20 years. And can be either experiment and theory. We have 2 experimentalists here and 4 theorists. And so we have a good mixture. And each one of you are going to have 3 minutes. And so let's start from here. You got to, yeah. So we're going to start from Professor Sakar.
Okay. Can you hear me? Yeah. So first of all, I'm really honored to be on a panel with such a breadth of interest. So hopefully we can speak to a broad set of passions about what drives us in physics. But I actually want to quote something that Pablo Picasso said, arguably the most creative artist of the last century. He said, "Good art is what people want to see. Great art is what people did not know they wanted to see." And I think that does resonate with us all, because we of course are all professionals. We write grant proposals and applications of various sorts, and you have to put down milestones and deliverables. But always in our heart of hearts, we hope to find something that we had not actually put down, and that the grant committees had not ever thought of, right? And this is why, as a side note, I'm not particularly thrilled at the idea of AI doing anything for fundamental physics. It will pretty do a lot for mathematics, which has well-posed problems, but physics problems are rarely as well-posed as in mathematics. And so I think that we are not yet out of a job. That's the first thing. With regard to a fundamental problem that I certainly hope will be solved in the next 20 years, it is something at the interface of the two, perhaps arguably greatest creations in fundamental physics in the last century. One is general relativity and the other is quantum field theory. And that's the notorious cosmological constant problem, which Steve Weinberg memorably called the bone in our throat. And that's a serious problem because in essence, what it says is that if we believe quantum field theory and the fact that fields have zero-point fluctuations, and if we believe Einstein when he says that all energy density must couple to gravity, then inevitably the quantum vacuum must couple to gravity, and essentially it would have stopped the universe from ever existing, an old universe such as we live in today. So our very existence testifies to the fact that we are missing something really big, some very fundamental reason why the quantum vacuum has not caused the expansion of the universe to reverse and go back to the Big Bang or go into eternal inflation, neither of which corresponds to the large, old, slowly expanding universe we find ourselves in. And although this problem has been recognized for nearly a century and the best minds have looked at it, to put it very bluntly, nobody has succeeded. And so when young people think that everything has been solved, there is nothing for them to do, I can tell them that there is everything for them to do, because I suspect that the cosmological constant problem, its resolution, will in fact open up a completely new chapter, such as not been anticipated so far, notwithstanding all the wonderful things that we heard about today. And I'm really hoping that well, you said 20 years. Indeed, we all hope to live another 20 years, and I hope to see the solution. But I want to add something more, if I might have another 30 seconds. This problem has not been solved, as I said, but in recent years, in the last 2 decades, it has been made worse by astronomers telling us that they have observed the expansion rate of the universe to be accelerating, as if driven by a cosmological constant or vacuum energy, but at an energy scale far, far below any fundamental scale in physics, totally unphysical. Now, this is something that we have been working on, and in fact, I'll talk about it tomorrow to show that this acceleration is in fact not the same in every direction. It violates Lorentz symmetry. So it cannot be due to the quantum vacuum. But that still leaves the original cosmological constant problem unsolved. And at least we can now focus on it rather than try to argue for a very fine-tuned value of this cosmological constant. It may well be zero, but that is no less a problem for that.
So let me sharpen your prediction a little bit.
Yes.
So basically you're saying that it is probable that in the next 20 years, we're going to solve a cosmological constant problem.
It's a hope, because certainly in the past 20 years, so for example, we have distinguished string theory colleagues there who have been talking about the landscape and the swampland, etc., which also tries to address this. But in my view, the anthropic solution is not a solution in very good taste.
Let's come back to this problem later, and let's pass to Professor Liu. And what is your opinion?
Well, I really hold to what was just said, that I can tell you what I hope for. But probably the really great stuff is stuff that I don't even know to hope for right now. Okay, and I have no idea about the time of anything. I'm terrible at keeping to time on anything. So I would just say that what do I hope for? One, of course, is something that I brought up, this whole tunable matter and developing unifying frameworks for that. But I think there's another problem, which people have made some progress on in the last 15 years, 20 years, which is physics far from equilibrium, statistical physics far from equilibrium, many body systems driven far from equilibrium, far from a steady state even. We really lack the frameworks. There has been some progress, and I really hope that we will start to develop the frameworks for handling these systems.
Can you be a little bit more specific what progress you wanted to see?
So, for example, there have been frameworks for generalizing thermodynamics and statistical mechanics, to systems far from equilibrium, fluctuation theorems and that sort of thing.
Establish dynamic equations?
No, often the dynamical equations, continuing equations or, field equations sometimes can be there, but then to look at the behaviors that come out, at the collective behaviors and try to just organize them, we don't have very good ways of doing that. So that, I really hope that we will develop that.
Okay, thank you. Well, our panelists have been very conservative so far. Maybe we, I said something in the beginning, make them making a wish list instead of making a prediction. So now we have Professor Wang, and so can you make a prediction instead of a wish list?
I have 3 predictions. I think
Okay.
you'll be happy with.
You are only limited to 2, not 3. Yeah.
So first one, which was going to happen for sure, that within 10 years, we are going to completely understand neutrino oscillation. It will happen.
That's a great prediction.
Second prediction, which probably will happen within, say, 20 years from now, is the discovery or undiscovery or disproof of the neutrinoless double beta decays.
That's another great prediction.
Third one, which there's a hope, it's a wish list, and may happen after my life, which is that the Higgs may not be a point particles, and we need the Higgs factory to understand the properties of Higgs, which may not be exactly the prediction from the current standard model. You may find some deviations from that.
Thank you very much. These are very, very interesting and bold predictions, and certainly will motivate a lot of young people to move in that direction. And so now let's come to Professor Wen. And what is your bold predictions?
Yeah, it's hard to make predictions because I think the really new theory is usually unnamed. The whatever have a name is not new already. Let me share some of my experience on these quantum Hall states. 35 years ago, studied these quantum Hall states, which are purely a quantum many-body system. At that time, I know the name quantum Hall states are just spin liquid, but I have no idea what is the internal structure. It's a mess. It's a soup. It's just no clue. And I think that's a good sign. It's a good problem. When I have no clue, no name, and then it's like arts. You provide a blank white paper, you can draw whatever you draw, name whatever you name. And as long as you make a story, and so after 30 years, when I look at quantum Hall states, I no longer view this as a disordered liquid. It's like a crystal, have a lot of internal structure described by category theory. So then the question is, then what is the other system which have no clue? It's a mess. And this is strongly correlated to gapless states. The quantum Hall state have energy gap is much simpler, and the gapless is much more complicated. So that's another thing which have no clue. So maybe we can make a progress on that. And but those are really a pure quantum system. And there are open system with a dissipation, interaction with the environment, and it's a classical system. Actually, like this, as everybody also ask, what is the internal structure of a neural network which works? And again, that's something I have no clue. Everybody say it's a black box. So maybe that's a good problem, and maybe there are some structure in it. That's what make it works. And but one need to really form a good story. So I feel that those clueless area maybe is a place you may have a really revolutionary new theory. But I'm a theorist, so I only make us predict what kind of new theory are there. Yeah.
So let me sharpen a little bit again your prediction. That is, there are going to be surprises. There are going to be something you look at it right now, and then in 20 years, all of a sudden you realize there's some deep secrets in there. That's a very safe prediction.
No. Actually, as a prediction, really, that right now for the pure quantum system with energy gap, we now be able to produce a list. What are they? What's the classification?
Okay.
I hope in 10 years or 20 years, we are able to provide a classification of this gapless system. Basically, it's classification for quantum field theory.
Okay.
It's really
okay.
critical.
So
then for the open system like a neural network or some dissipated quantum system, I have no clue. That's even more far out.
Thank you for clarification. I understand much better now. And Professor Wen said he hoped to produce the classification of the quantum phases, and so this is certainly an extremely important task. And Professor Uguri.
So thank you. So, it's me?
Yeah.
Okay, yeah,
it's you.
thank
Yes.
Thank you. So, Shandong actually gave us 3 to 5 minutes, and so I thought I needed to say what I want to say quickly, so I prepared text. So allow me to read. So in my concluding remark at the Strings 2026 in Shanghai last month, organized by Professor Yao, I discussed a list of open problems, in fact, that might plausibly be solved within next 10 years. So tonight we have 20 years, so I can try to be more ambitious. So the breakthrough I'd like to see is a satisfactory mathematical definition of quantum field theory in 4 dimensions. Now, for those experimenters here, this may sound formal and far removed from experiment, but I believe the opposite. So quantum field theory is a basic language of particle physics and is indispensable in like condensed matter physics like Xiaogang does, cosmology, like Sui does, and many other areas. And deeper formulation could provide new tools for strongly coupled phenomena from confinement to quantum phases. Quantum field theory emerged in the late 1920s from the unification of quantum mechanics and special relativities. As its centenary approaches, we still lack a framework broad enough to encompass the situation physicists actually care. Together with construction of a central 4-dimensional example, the most prominent case is the construction of 4-dimensional quantum Yang-Mills theory and the proof of mass gap, which is one of the 7 Millennium Prize problems. The situation reminds me of the history of calculus. Newton and Leibniz created the calculus, and Euler and Bernoulli family used it brilliantly before even its foundation was secure. In the 19th century, Cauchy, Weierstrass, and others placed calculus on firm ground, and then the mathematical rigor expanded its reach, reliability, and power. Quantum field theory can be considered as calculus on infinite-dimensional space of fields, and we differentiate functional, integrate over fields, often with remarkable success without firm ground. A sound foundation could organize these operations coherently, strengthen existing methods, and reveal questions beyond the reach of present techniques. If the history of calculus is any guide, this would open new era for fundamental physics. Several routes look promising: lattice gauge theory, constructive and operator algebraic method, and more recently, stochastic quantization through nonlinear partial differential equation. Professor Martin Herr was here earlier this week, and he's a leader in this area. They have produced rigorous construction of important low-dimensional models and substantial progress on gauge theories. The eventual framework may draw on several directions, on ideas we do not know yet. Artificial intelligence adds a new source of urgency. The AI system have begun to make genuine contribution to research in mathematics. As we hear just yesterday, they made progress in Riemann hypothesis, including results on long-standing open problems. One reason, I think, is that formalized mathematics can provide exact feedback, as Bill said, with a proof assistant such as Lean. Proposed proof can be checked mechanically. So this supplies precise word signal for reinforcement learning. Although theoretical physics has seen notable AI-assisted results, quantum field theory as a whole offers no broadly available machine-checkable environment that can mechanically determine whether proposed non-perturbative argument is correct. Mathematical formulation eventually encoded in formal system can provide such an environment. It could enable human and AI to work together to explore non-perturbative dynamics, classify theory and phases, as Xiaogan said, and derive observables that connect to experiment. So my wager for the next 20 years is that the language of quantum field theory, which physicists have spoken so fluently for almost a century, will finally have its grammar written down. So as I mentioned at the beginning, quantum field theory itself emerged from the unification of quantum mechanics with special relativities. Once it stands on the rigorous mathematical foundation, even more formidable problem remain, which is related to your first question, the unification of quantum mechanics with general relativities, and what I might call the final boss of unification. That, however, is a subject of another day when the question is not about the next 20 years, but next century. So for now, I'm settling my wager for unification of special relativity with quantum mechanics.
Thank you, Professor Oguri. You talked a lot about quantum field theory, and I don't know how many students here actually took the field theory course. And one thing I heard very clearly, the field theory is a combination of quantum mecanics and relativity.
Special relativity.
Special relativity.
It's an important distinction.
So your prediction, if I understand correctly, that the next 20 years, there are going to be a significant theoretical advances in understanding quantum field theory.
Well,
Is that
my
correct?
hope is that finally, after 20 years, Professor Yao will recognize quantum field theory as a branch of mathematics.
Okay. That is a very specific prediction.
Yes.
And that we can see.
So, yes.
Thank you very much.
So maybe 20 years from now, we'll present the quantum field theory to you, and you can tell us whether it's now mathematics or not.
Okay, so let's move to another experimentalist, Professor Cheng, and you have 3 minutes.
Okay, I don't have a prediction either, and also have the wish list. Actually, my wish list just comes from the distinguished lectures I heard today, the 2 lectures. First is Professor Ivan Wang's lecture. In his lecture, he talked about 3 keywords, I remember. First, global. Second, neutrino mass. The third, Higgs link bridge to the matter and antimatter. Okay, if I remember correctly, okay, the word used. And first, from the global, we know recently we established the existence global, which is a direct proof of the non-abelian property of the QCD. And it's also the direct proof of the mass origin from strong interaction. Okay, that's very important.
Thank you,
It's the origin of mass from a strong interaction. And then if I talk about neutrino mass, we don't know the origin yet.
Right.
Standard model did not have the prediction on it. And then if I talk about the Higgs particle, which bridges the matter and antimatter, actually the matter, for the Higgs sector, we understand that how Higgs explain the origin of mass. Higgs gives the mass to the WZ boson, and how the Higgs give the mass to the fermions. We understand this, but we don't know how Higgs gives the mass to the antimatter. We don't know.
Thank you.
Okay, then this is first lecture. The second lecture I heard is from Professor Xiaogang Wen. He talked about a lot about unification. So my hope is we know this, the origin of mass from the QCD or from strong interaction, and don't know the origin of mass from neutrino, and don't know the origin of mass from the Higgs for the dark matter. So I hope in 20 years we can have a unified picture of the mass origin. Okay, this is my hope.
Thank you very much. Well, usually, in my mind, the experimentalists are more conservative. Theorists are more adventurous. But from what I heard today, that the two experiments have made very specific predictions. They're very bold. But all the theorists have been very, very vague about prediction. They provide a wish list. So therefore, I think they deserve to be examined further. We need to ask them more harder questions. They have to give up something, okay? So let me ask maybe some questions for the theorist. So let me ask Professor Sakai, why do you think a cosmological constant problem can be solved in the next 20 years? So what do you see in the other people have not that it has to be solved in 20 years?
Well, obviously, there is no guarantee that it will be solved in the next 20 years if it has not been solved in the last 100. But it is just a practical observation that there are far more young theoretical physicists around today than cumulatively over the last 100, I would say. And also, the problem has been much sharpened by all the people who have tried to solve it unsuccessfully. And so usually, or rather quite often, maybe not always, a problem, even if you fail at it, you contribute something to its understanding. And the failures are often just as important as the final success in solving it. So it is probable, not a guarantee, but it is probable that one of the many very smart people today who are considering doing something in theoretical physics that is not been done before, that is not just a little epicycle on something that has gone earlier, but a truly profound new discovery would be to find a solution. But what is already clear, because there have been so many attempted solutions, in fact, I know a student of Gerard 't Hooft wrote his entire thesis on all the proposed classes of solutions to the cosmological constant problem, none of which work. Right? And so if we have exhausted all the possibilities in our current toolkit, it stands to reason that if there is a solution going to be found, it will have to be something new, either some new mathematics, which has often been the clue to unraveling a fundamental problem in physics, or a completely new orthogonal insight from anything that any of us have come up with. So
in that regard, let me ask you the question. Is a null discovery also a discovery?
Absolutely. So for, in physics, it certainly is.
Okay.
It's the dog that did not bark in the night, as Sherlock Holmes told us.
So you're going to win anyway in 20 years. Yes. If it doesn't discover anything, you say, we have exhausted all the possibilities. If it discovers something, then you say, I know that I'm going to discover something.
Well, not quite, because although it is important that we learn something from not finding something, it is more fun to find something. I mean, we all agree with that, right? So let us hope that somebody will solve it. What I meant to say is that if we have failed to find the solution using any of today's tools, then clearly there is something new awaiting us, which would be necessary for its discovery. It won't be just finding an error in somebody's calculation or finding a new way to do the calculation. It will be something completely different. So in that respect, I hope to be surprised.
Okay.
And I just hope I understand the solution. So I should say at this point, David Gross, who is well known in this audience, once was giving us a talk in Copenhagen, and he said, my dog does not understand quantum mechanics. It's a very clever dog. It can, it sits up and looks at me when I'm talking to it. I think it understands what I'm saying. But if I tell it Schrodinger's equation, nada, no response. So it is quite possible, and we have to keep that in mind. We may not be clever enough to ever understand this problem. It is not the case that we have been given a guarantee that we necessarily can solve every physical problem that there is. But this is our destiny. This is our life. We must try.
Yes.
May I
Yes.
chime in? May I
Sorry?
chime in?
Yeah, of course.
So
Please.
I would like to actually point out that some of the fundamental mystery like dark energy and also the origin of mass, as Yifan and Sean raised, can be due to our very limited understanding of quantum field theory and possibly quantum gravity. Where after all, Higgs mechanism is a perturbative method in quantum field theory. And similarly, the question about dark energy, just one loop calculation of quantum field theory. There is much more to quantum field theory than this kind of perturbative calculation. Where supersymmetry was introduced because that was the only way we can think of to reduce the mass of Higgs and to eliminate cosmological constant. But this is by certainly not the only way that that can happen. Even more recently, for example, the discovery of general symmetry that Xiao Gan talked about opened our insight into even some aspects of standard model particle physics that we didn't know about. So I would like to return to my plea that one of the important things is to give more satisfactory understanding of quantum field theory, which can give us more powerful mechanism to understand some of these questions.
Okay, so you're saying that if we understand quantum field theory more, we might solve the cosmological
It
constant
might
problem.
give us more mechanism. I mean,
Okay.
we have this puzzle because we have tried to come up with a model to explain nature with a limited understanding of this unification. But if we we have better understanding of what the theory we are talking about, we certainly will have more powerful tool which can actually solve some of these problems.
That is a very good point. Professor Wen, do you want to make some comment along this line? Okay, so maybe I probe Professor Liu with a question that you give a wonderful lecture today. I learned a lot from your lecture, and by tuning the connections, you can produce very interesting behavior. But your prediction is about open systems. And are these you call open systems, or what do you think the most interesting thing going to happen with the open systems? And what's something you want to see the progress in the next 20 years?
Yes. Yes, I would call these open systems. I think that what's going to be the most interesting thing? Honestly, I have no idea. What's going to be the most interesting thing in the next 20 years? I mean, I wish I did.
Yeah.
I mean, all I can do is to say, okay, and systems, we have made tremendous strides in the last 20 years on a number of different kinds of open systems. So for example, in systems where the underlying equations break time reversal symmetry, our main methods for looking at these things are hydrodynamic equations. We go to low wave vectors, low frequencies, and say, okay, what the Navier-Stokes equation is an example of that.
Yes.
And when you break time reversal invariance, then you have extra terms. You have terms in these equations that are
Yes.
normally not allowed, and that so now we can understand these, and this starts to give this a way of starting to develop frameworks for things. But then you take these equations and then you push them. Just as you take the Navier-Stokes equation, you push it to turbulence,
Yes.
And all hell breaks loose, right? Again, in turbulence, there have been great strides. So in any of these systems, you can find that, yes, there's been great progress. What there hasn't been so much is to take that progress and really put it together.
Yes. So you're saying that with the open systems, that there's so many phenomena that happens.
And there's so
you
many
learn a
different
lot from
kinds
this,
of open
different
systems.
kind of phenomena. So you can learn a lot from that.
Yeah.
So that point is certainly well taken. Yeah. Open systems is probably a big future frontier in physics. So maybe let me go to Professor Wen. Your lecture is also extremely interesting. It makes us to think, what is fundamental? Because, particle physics, we're trying to, reductionist principle, we try to use simpler and simpler things to explain. And then you have the string liquid. And, the liquid, we usually think is very complicated, right? And so now, are you trying to using a more, many degrees freedoms to try to understand simple electrons and photons, we call them elementary particles. So can you give us a feeling that in your mind, what is fundamental? What is a fundamental breakthrough?
Okay. Yeah, actually, this is a very interesting question. What is a fundamental? In some sense, there's two different ways we look at a word. That is, some people, when you look at the rope, they say, oh, this rope is formed by certain molecules. That is a component, is a key to understanding. And another person look at the rope, oh, this rope go around the loop have knots. So they pay more attention to the structure or organization. And so from these two different philosophy, I myself is more inclined to the second one, that is the structure organization is more fundamental than the components, whether the smallest component is not an issue in some sense, because the most basic building block of quantum mechanics is a qubits. That's already known. So the richness of word coming from the organization. And so in that sense, the organization became more fundamental or more interesting. So therefore, from this line of thinking, I will make a theoretical prediction. That is, in 10 years or 20 years, maybe category theory will be as popular as a group theory in theoretical physics. So this is a very concrete prediction. Yes. Whether it's fulfilled or not depends on the young people here, whether they want to go into that direction. And the reason for that really is that the organization, what is the mathematical framework to describe all kind of organization looks like the category theory is a nice fit for quantum organization. Then you also raise question about the open system. That's another thing I like to see, that the open system have different organization principle. And you can have a purely classical open system. And now the quantum computer gave us something in between. Some quantum lousy quantum system actually can be viewed as a quantum open system. And that may also have a different organization principle. So then, because there's a machinery, the system is there. The quantum computer is a quantum system with the dissipations. And the understanding there's a quantum device and their organization may have a. I really feel that's a new area which is really worth to exploring. And as another experimental prediction is that we're talking about a certain organization may give rise to wave satisfying Maxwell equation. I wish maybe I will predict in 10 years or maybe 20 years, we'll find a quantum material which produce Maxwell equation, have a wave satisfy Maxwell equation. So that's a fulfill Maxwell's dream, 150 years ago. Yeah.
Thank you very much. I think that Professor Wen made his predictions much more clear than the first time that I heard, and I really thank you for that. And finally, let me go to Professor Oguri.
Actually-
And I
Actually,
certainly
can I
Huh?
just
Sure.
can I
Yes.
just
You can ask
follow
him
up on
questions.
this?
Yeah.
I also want to follow up on this because, you know, this question of what is fundamental.
Yeah.
I think you see a sort of difference between those of us who are condensed matter versus the ones that are not. That it's the more is different idea.
Yes.
You know, the idea of emergent phenomena being very fundamental and needing organizing principles and frameworks, and versus drilling down to the few, and this is where I think there is this progression from what happens at the smallest scales to the collective scale, and then I was talking about the distinction between conventional condensed matter, where more is different, but many more is about the same as more, versus systems where many more is different. And I don't know what goes beyond that, but I think that's quite enough to deal with for now. Yeah.
I really like your comment because it makes me think that when we speak about fundamental, actually we mean different things. When particle physicists mean fundamental, they're looking at the fundamental constituents. When the condensed matter talk about fundamental, they're talking about a phenomena, okay? And they're not take this apart. And so maybe we can build a bridge, between the fundamentals in the different area. Yeah, I really like that comment very much, and it helped me to understand what really fundamental means. So let me go to Professor Oguri, because I promise I'm going to try to make theories to pay for their, not making very sharp predictions. I certainly resonate with you that, quantum field theory is fundamental, and yet, the field theory textbook is filled with perturbation theory, plane waves. And there's a lot more physics beyond plane waves. And you mentioned confinement, for example. So many of the quantum field theories, if they're non-perturbative, they can be solved in the computer. For example, simulating lattice QCD. What kind of thing you could be looking at, you think is really helping you to understand?
Well, for example, you say that the non-perturbative quantum field theory can be formulated on the lattice. But for example, there are things you cannot do on lattice, like time-dependent things. So how is, for example, the quark-gluon plasma behaves in time-dependent way? How can you calculate, for example, the two-point functions and apply Kubo formula to derive some transport phenomena?
Okay.
So those are beyond the current reach of lattice gauge theory. So you are expert on this subject.
Absolutely. And there are a lot of very non-perturbative phenomena can't be calculate using the current lattice technology.
So I think that there is even though lattice gauge theory has made very impressive progress and obtained results that are remarkable, however, it's not everything. Lattice gauge theory alone will not answer all the questions about quantum field theory. I just give an example of transport phenomena, for example. So I think that, but more broadly, in the case of calculus, I gave an example of calculus. The formulation of calculus in 19th century, Cauchy, Weierstrass, gave us totally new world of mathematics that you can explore and bring in new techniques. And so that's what I'm looking for.
Okay.
In related to that, actually, I would like to raise some question to Xiaogang, because I enjoyed your talk about SpinNet, and I really felt this time I understood what you're doing. But these spin networks are propagating in a fixed space time. So I wonder, you shouldn't one consider formulating the situation where information, the space and time also emerges from information. And I think that this kind of question can be part of the question that can be addressed by more fundamental formulation of quantum field theory, quantum gravity, etc.
Could I ask him a question about that?
Yes.
So, Hiroshi, just to press you on this, as you know, in the 1930s, 40s, 50s, there was a program of axiomatic field theory pursued in Europe,
right,
which came to nothing.
I agree.
So, in what respect do you, just to press you for a bit of fun, what respect do you say that the mathematically sound formulation that you seek now would differ from the aims of those people?
I think we learned lots. Well, first of all, in order to make progress, we need to know lots of examples. Certainly, in the program in the 50, 60, was that we have very limited understanding of quantum field theory, what quantum field theory can do, both theoretically but also experimentally. We have very limited understanding, and the trust of quantum field theory was also very limited. And I certainly don't think that axiomatic approach alone would solve the problem. And now, first of all, there are two things going on that makes me hope that 20 years from now that we will address this problem. First is that we now, thanks to the progress in the last 50 years or so, we know much more about quantum field theory in depth, especially in the area of supersymmetric field theory. We know many phenomena of duality, Seiberg duality, S-duality, etc., that we didn't know when axiomatic people were working on it. And the second thing is that there are actually some promising new direction. This stochastic quantization based on nonlinear partial differential equation is one of the directions, which has been actually successful in some of the examples in 2 and 3 dimensions. So that's very different from some of the early axiomatic methods, where the examples are very limited. So I think we are actually in a much better stage to come back and try to work on this problem, I think.
Thank you.
Thank you. Are there any comments?
Yeah, there's a saying that if you are a hammer, then everything else is a nail. So I'm kind of play this rule because I've been working on condensed matter system, which is basically a lattice system. So to me, that everything is a lattice system, including quantum field theory, which is a little bit the opposite what Rushi started. But I try to put in some another perspective. In quantum gravity, there is a landscape Swampland theory, which is there is a quantum field theory which is compatible with quantum gravity, and that's belong to landscape. There are also quantum field theory which are incompatible with quantum gravity, but that's Swampland, and which is kind of illegal. However, in condensed matter, there's a similar situation. There are quantum field theory which is compatible with a lattice model. They are low energy size theory of a lattice model. I call that a condensed matter landscape. There are quantum field theory which are incompatible with a lattice model. More generally, it's incompatible with the UV cutoff, UV completion. And that's belong to the condensed matter Swampland. So actually, this new mathematics I'm talking about for the gapless theory is really about this. So starting from a lattice model, what a possible continuum limit that can possibly have that belong to landscape. So that's give rise to a class of quantum field theory. We call them legal or belong to landscape. And then this axiomatic quantum field theory, I feel that I don't want to shoot. I feel too not modest. I said, when I was in Princeton, I took a Whiteman's course on this formal quantum field theory. It's very frustrating. It's very complicated delta function, this cutoff of this. But now, when looking back, I feel that that quantum field theory have a basic assumption that it's a theory on the manifold. I feel that may be a mistake, to be, boldly, I really feel that the manifold is a very strange object, and if using that as a starting point is making things very difficult. However, if you do the lattice or with some UV cutoff, then this whole thing will be under control. But nowadays, I really feel now is time to go back to this axiomatic quantum field theory and those general symmetry and etc. I think would make a progress, but not based on manifold, based on more operator algebra without introducing manifold. That's maybe a way to go. Yeah.
Well, I enjoy this discussion, but we don't want to turn that into a quantum field theory discussion class. So I think it is time now let our audience to ask them questions. So let me open this to the floor. So anybody want to post a question to a panel member? It has to be a question. End it with a question mark. And anybody want to try? Yes, we have someone over there. Oh, here. Yes.
Excuse me. I just want to ask one question because Professor, when you just said that the theory on a manifold is weird. So why do you think so? Because maybe I haven't learned so much knowledge. So I want to ask this question. Thanks.
Is that question about whether the theory on the manifold is not a right approach, or something like that?
Can you repeat your question?
Yeah.
My question is why a theory on the manifold is strange for you?
Actually, this is it's already experimentally proven there is no manifold. The reason is that the fundamental property manifold is that you have 2 points which can be as close as possible. But however, to observe these 2 very close points, you need a very high energy photon. And when the 2 points is too close, like below this 10 to the minus 33 centimeter, the photon with such high energy would make black hole, which is bigger than 10 to minus 3 centimeter. So this is to me, this is an experimental fact that the manifold simply do not exist. It's an emergent phenomenon as an approximation, not fundamental construct of the theory. So
because of the gravity,
because of gravity, exactly. Really, that's quantum gravity. So certainly, if you do not touch quantum gravity, then manifold can exist. Actually, this is just like the Navier-Stokes equation exists if you don't touch molecules. But we know fundamentally they are really molecular dynamics. And so it's really about the quantum gravity, really about emergence of manifold, starting from something discrete, which is a very wide open question. I think string theory have a lot of insights in that direction.
So in physics, we always have approximation. Yeah. So in certain approximation, manifold concept certainly is okay.
While I enjoy this discussion, I think I will bring the question to the theme of today. That is the prediction for the next 20 years. Can we have the next question related to the theme of the discussion today?
Hi, thanks for the very interesting discussion. I'm a little greedy, so I'm going to direct this question to maybe all of you. Okay, because well, we all know like AI is already transforming a lot of physics research. So in line with the theme of tonight, I'm wondering like what do you think, like in what way might AI transform the current way of doing research in your like expertise or in your separate field? I mean, presumably like by changing the way people do research, maybe that will lead to more interesting discoveries.
May I, turn the question into, may AI help us to make a fundamental discovery? How's that?
Yes, but maybe like from, in each specific field, like there might be some differences, and I'm wondering like, what do you think of that from each of your individual perspectives?
Okay, so yes. Anybody like to answer the question?
If by AI you mean machine learning, that is already helping us, and it is crucial and essential to making fundamental discovery. Nobody disputes that. And machine learning has been used certainly in particle physics and astrophysics and condensed matter for at least 20 years now. So it's not, I mean, the pace might be accelerating, but the concept is not new. I guess you are asking about something else. Is AI going to actually frame or formulate new questions? About that, I'm skeptical, but some of my colleagues may not be.
Any other panel member like to?
Well, okay, let me say that AI has definitely inspired my field of research a lot. The whole idea of tunable matter, a lot of the underlying concepts really come from what we have learned from AI. And, you know, this is what led me to think about biological systems as tunable systems, much like AI networks. So I think, you know, I certainly owe a considerable debt to the concepts underlying AI. Now, AI itself, to what extent is it useful in asking questions and making fundamental discoveries? That I am more skeptical. I feel that because, you know, our business is to ask questions that are really, really different from other questions that have been asked before. That's not something that AI is really good at.
Right.
And fundamentally, you know, the way our brains work is so different from the way large language models work. That I think the things that large language models are good at are different from the things that our brains are good at. So just let's take one example. I talked today about the energy usage, but another big difference between brains and LLMs is that we train our brains on very little data, right? Whereas the LLMs are basically trained on all of the text that exists in the world. So these huge differences mean that there are really real differences in the way we learn, and therefore they're just differences in the way we do things.
Okay. More comments?
Yeah, I think AI is a great tool. It will improve significantly our working efficiency and also improve the so-called pattern recognition capabilities and also signal background ratios. Yes, maybe AI can help us discover some signals from huge background. In that sense, yes.
Okay, we have some consensus here.
Maybe let me tell a story first. It's, you know, I've been working on some math-related physical problems, so I was invited to give a talk, a seminar in some mathematical institute. And the host kind of got worried and warned me that please give a clear definition of what you talk about. And then I said to myself, if I know the clear definition, what I'm talking about, I have nothing to talk about because that's no longer physics, that's became mathematics. And so actually, what I really mean is that the physics maybe I would say mathematics maybe similarly, you know, there's some part of research you work on not well defined the problem, and the goal of research is to come up with a clear definition, which completely fix the structure of the answer. And then, so sometimes we say that once you come up with a clear definition, the rest is the mathematics. But that's maybe not very precise. I should say, nowadays I should say, if you come up with clear definition, the rest is AI. So what I really mean is that maybe the powerful AI may change the mode of research. That maybe the more creative research of figuring out what are related, what are relevant, what can be connection, to come up with a definition. Then once you come with a definition, you just give that to AI. Then the AI would produce all the logical consequences from your definition. But so in this case, to knowing what are relevant, what are connected, those unknown things maybe emphasized more. And the things which can be logically derived. Then we have a more powerful tool. Just like after Mathematica, I feel I don't need to practice doing integration, because when I was in college, I practiced 1,000, maybe 10,000 integration. I thought that's a black arts that make me very powerful to be able to do all kind of integration. Now I'm things are very silly because I can use Mathematica to do that. So I don't know whether AI would play similar role. Yeah.
So if you worry about, to find a job as a physicist, don't worry that AI is going to take over your job. You're still needed. So, well, in the interest of time, let's have a final question, actually, specifically for the 20-year prediction. Anybody like to ask that question? Yes, here we go. Yeah, we have.
Okay, I have a question for Professor Wang. So we know that over the past few years, we have seen many examples that gives us precision measurements that differentiate experiment and theory. Sometimes up to 5 sigma. The most recent one that I can reckon is also related to my field, that's QCD, so mu1 G minus 2. And after like 5 years of theory and experiments, we finally find that their difference converges. So my question is, given that in the at least in 5 years, it's impossible to increase the energy of the accelerator by much, how confident are you that in the following 20 years, we find something that really differentiates theory and experiments by increasing the precision of experiments? Thank you.
Professor Wang.
I think G minus 2 is a different example, which if there's any, say, new physics, basically I believe there's no model and you don't know what is the energy scale. So it's just a deviation. However, for Higgs, it's very different. Higgs, to be honest, is a very, very special and strange particle. It's very different from anybody else. So having a very precise measurement of Higgs with its coupling with all the particles and visible or even invisible is very, very important. Indeed, we have this problem of natureness. Of course, you can argue you can have no new particles all the way up to Planck scale. This, of course, is one possibility. But there is there's a pretty high probability that there should be some cutoff at the level of, say, between 1 to 10 TeV. And if that exists, it should be seen by the Higgs factor. And on the other hand, we all know there could be a dark sector, and among all the elementary particles, Higgs is the most probable particle which has something to do with the dark sector. So that's exactly why the international high-energy physics community, we all agree that Higgs factory is what we want, the next machine, unanimously across all the countries. Of course, we cannot go through all the details. There are, thousands of pages of papers talking about this. I think that's really what we should go, whether in China or in Europe or in somewhere else. And I think that's a step for particle physics we cannot skip, and should be done sometime and somewhere.
Thank you very much, Professor Wang. This is very encouraging. And any panel member would make some 10-second last word? No?
I second him.
Yeah, 10 seconds.
Just to follow up on the question you asked, it's a good example, the G-2 of the muon, of where the increasing precision of the experimental measurement spurred the theoretical community, especially the lattice community, to calculate a particular contribution, light by light scattering, better than it had been done earlier. And it so happened that it actually reduced the discrepancy rather than increasing it. It could have gone the other way, right? But the point I think to note is that the physics community accepted the answer. It is not necessarily the answer that most of us wanted to see, but we accept it because that is what nature has chosen. And, you can't cheat with nature. You have to accept the answer that is there, regardless of whether we like it or not, whether it is good for the next funding proposal or not. And so I think one thing that we should stress always is that we are not in this for the money. We are in this to learn the truth. Yes.
I think this G-2 is a very special example here now. There were a lot of experimental measurement, and only one which is now remove this discrepancy, and together with lattice calculations. And from, let's say, experimental point of view, the standard is a little bit low to say that there's no discrepancy. Indeed, in BPC2, we're going to upgrade our machine to have a much more precise measurement of the R value, which can actually pin down the problem and give a clear answer whether this discrepancy of G-2 is really exists or not.
Yeah, I agree with Professor Wang that there are still mysteries with G-2. Even lattice QCD calculations has not been done with precisions that, it should be. And we should, maybe in 20 years, we're going to solve that problem. No. Okay, 5 years, 5 years. Okay, well, I thought lattice QCD calculation usually taking decades to get good precisions. But again, that this discussion reminds me that making prediction is hard, especially about the future. However, that today we have had some very important consensus, and AI is not going to replace physicists, right? And quantum field theory is one of the most fundamental things, even though the emergent phenomena is teaching us a lot and maybe become fundamental as well. And dark energy and maybe dark matter as well will be some of the most important to watch out for the next 20 years. And again, double band decay and Higgs bottle. So we have gone through a lot of very interesting topics. So let's thank all the panelists with a round of applause. And enjoy the rest of the evening. Thank you very much.